Okay, we can get started. Welcome to this JuliaCon session. Luca Ferrante will be the chair for this session. Our first speaker will be Guillermo, and he will talk about the debugging time spent in LLVM with Snoop Compile. Please join me in welcoming the speaker with a warm applause.
Well, thank you very much. I think you can hear me well. So today I'm going to talk about measuring the debugging time spent in LLVM with Snoop Compile. A quick introduction, I work at a company called PSR, and we do a lot of energy modeling, and we are heavy users of Jump and Julia since 2016, I think. And so, well, we do a lot of advanced tools for energy systems, and we are currently doing like many production systems in Julia. And some of our clients use some operation planning, generation expansion, portfolio optimization tools written entirely in Julia and Jump. And each one of those tools has evolved over time, and some of them have more than like 80,000 lines of code. The other ones have like 40,000, which are kinds of big applications in Julia, in my opinion. And they started a long, long time ago. And so when I got to PSR, some of those applications were already mature enough, and developers were there for a long time. And there has always been a complaint about time to first run of those tools, especially when developing. Because when we deliver this to our clients, we usually only use package compiler, and at the same time, well, this problem is limited to developer experience. And for developers too, usually you just turn on revise, or you run Julia with some tricks in compilation. You turn off the optimizations, and you compile the minimum amount of code possible. So it's quite fast to deliver and to develop using those tools. But it was always something that tricked me. Like it annoyed me so much that when we run with the standard compilation and optimization switches, it took some time, like 3 minutes, to have the first run. And then I started my journey with Snoop Compile, and the first flame graph that I plotted was something like this, where you have like this huge blob in the left, where I'm pointing to, you're right, probably. Yeah, no, you're left. With the type inference, this like huge valley, which is LLVM time doing compilation, and this small other inference time at the end. And so I started digging into the code, and digging into the rabbit hole, I found a lot of type instabilities that have been there for a long time, and some unnecessary specializations. So one example of it is that we had a function called open. I changed a little bit the types, but the idea of the function is this one. And this open function was specializing for 300 different functions. And it was taking about 11 seconds only to like do the inference on these functions. And this sucks. There's a lot of time spent, and like it annoys me so much. And so with some small adjustments, we got like a no specialized wrapper into the function and things like this. We come around to like, instead of 3 minutes, now it's 2 minutes 30 in the same case. But even with some other ideas in mind, I decided to try to dig deep into it and see if I could measure the time spent in LLVM. And then I searched into a random issue in Snoop Compile, and I found that this macro existed already. It was not just that well documented, but there is a SnoopL macro that allows you to measure exactly the time spent in LLVM. And this is the goal of this talk, is to bring the attention to everybody that you can do this and you can measure the time. And so, well, it's a very simple script. It's a very simple way of doing it. You just call the SnoopL function, and you pass these two files, these func names and LLVM times.yaml. I run all two. I changed a little bit the name of the package because it's a proprietary software, and I didn't want it to disclose everything. And well, when you run this, you gather these two files, and with this very small script, you can understand exactly how much time each function spent only compiling the LLVM code, only like doing the LLVM step. And then the first time that I did this, I saw a lot of functions that were spending more than 1 second only to generate the LLVM. In particular, there is this one function that spent 10 times only generating everything. So this is a big red flag that something's very wrong with the design. And then it took our attention, and we started to do a bunch of refactoring, and most of the parts that spent a lot of time in LLVM is just that some functions were like 1,000 lines big, which makes no sense. And you should follow the performance tips in the Julia documentation. And we still have some more than 1 second LLVM times in this situation, but like right now it's much better, and we really put some thinking into it, and it's really possible to redesign your code to be more type stable and to spend less and less time into inference and LLVM. And right now, for this particular model, the time to first run is 1 minute 15, but like it annoys me less right now, and we can still improve it. We have new hires, and some of them are working on this. And well, as I said, the goal of this talk is just to like point it that if you're having time to first run, time TTFX, you can go one step further and don't stop at inference and go to try to measure LLVM times. And sometimes it is a very direct search, because it points me directly to the method. Like this method in particular is very, very bad. So that's the main idea and main advantage of this tool, that I think it's not that well advertised for the community. And so my conclusion is this: well, the SnoopL is a great tool to understand where your code base might be not healthy. It's a great indicator where you have like pain points in the code base. And we used all the tools described in Snoop Compile, the Snoopy, to measure all the type inferences. You use Chukutlu to go down into the inference calls and understand the type stability of the code. And this is really, really helpful. And well, you should definitely follow the performance tips written in the Julia documentation. That's the talk. Thank you very much.
Yeah, thank you for the talk. We have time for a couple of short questions, if there are any. Yeah.
So, how actionable is that output? I'm not used to digging into LLVM, so that name add constraint 2 doesn't mean anything to me.
No, it actually is exact. Now it doesn't mean anything because I changed the name, but it is like it's actually the name of your function. It's Julia underlined the exact name of your function, and it's very easy to dig into. And like as soon as I saw the 10 seconds, I said, "Oh well, obviously this is yes."
Is the time that is measured all of LLVM or primarily the code generation to LLVM? And how useful would you want to expose timings at like LLVM pass level?
Like I think this is only the LLVM pass levels. Because in the YAML file it has like the number of code blocks at the beginning and the number of code blocks at the end. So this is only the time spending in LLVM optimizing. It's not the code generation. I think the code generation for the code was fast. I mean, it helps every time that you have more information, but I was happy with this analysis. I was pretty happy.
Do you have any other questions? Yeah.
How do you choose which functions to soup, and would it be useful to have a tool that can insert the annotations?
Like in our particular tools, like since we package compile, most of them we have a single entry point to a path or a folder with a bunch of files, and then we just chose this one and it propagates inside, so we can measure anything that gets called inside. So in our case, it was an easy decision because you only have one main entry point for the whole application.
If there are no further questions, let's thank the speaker again. And our next speaker is Carsten Bauer, who will talk about pinning threads to CPU cores. Let's welcome the speaker.
All right. Hello, everyone. My name is Carsten Bauer. I work for the Paderborn Center for Parallel Computing in Germany. And in my lightning talk, I'll talk about pinning threads to Julia, my package threadpinning.jl that I created basically out of necessity when writing a physics code, like a quantum Monte Carlo code, and there was no good option available. So that's why I'm here now. But first steps first, why should you care? Like, why should one pin threads? At least there can be 3 reasons. One is it can dramatically influence the performance of your application. I'll show an explicit demonstration in a second. It can be useful to reduce the noise in benchmarks. You have like more stable conditions overall. And thirdly, another talk that I gave a talk last year about liquid.jl, a package for hardware performance monitoring. And that package really relies on threads running on certain cores because with that tool, you look at performance counters within a certain core to measure the number of flops and all kinds of interesting metrics. And if your threads would migrate around, you know, you would just have to compensate for the migration or just measure garbage. So those are 3 reasons. What is threadpinning.jl? Again, it's a package I created to pin Julia threads systematically, interactively. You'll see an example in a second. But also, while writing it, I realized that it would be nice to query and visualize the system first, right? So that you see what you're actually pinning to and if that's what you want. So that's another aspect of the package. It can do many more things than just pinning the Julia threads. It can pin open blast threads. It even checks whether your thread setup makes sense, like that it's not completely, you know, optimal. And there's also tools in there to measure core-to-core latency, you know, generate some nice plots. All came later. Many more tools that many more features that I can't mention here, but feel free to ask me about it later. There's one big limitation right now. I mean, not big for the audience. We just saw the Julia survey, and the most used OS is Linux. So it works on Linux, but currently it only works on Linux. Sometimes for fundamental reasons. So macOS just doesn't allow you to properly pin threads. And Windows, there's a PR for it. I'll come back to that later. Right, so but you might say, why create a tool for that? There are a couple of tools to pin threads, right? So, you know, I mentioned a bunch of here, taskset, NumaCTL, LiquidPin. LiquidPin is the first one I tried because it's part of this Liquid tool set that I mentioned a second ago. And the problem there is, first of all, it's not interactive. I want to use these tools in classes for teaching and so on, so I want to do this out of a Jupyter notebook. I will play around, run the same code with different pinning schemes. Those tools work in the command line, so that's problem number 1. But the most important problem is that they might not give you what you want or might not work with Julia. And that's mostly because Julia spins up more than just your Julia user threads, but also some signaling threads or the blast threads and so on. So these tools don't know which threads you actually want to pin. Right, I gave a task set example here. So in that case, it does the right thing. It sets a process affinity, so your code will only use the cores that you indicated. But some Julia threads might run on the same core twice. You know, they are not ordered, right? So you can't rely on that. And thread pinning will be a solution for that. There's one built-in tool that I want to mention, which is the Julia exclusive variable. You can set it to 1. It gives you like this natural ordering, first thread to first core, second thread to second to core, or I should say CPU thread to be more precise. It's good that we have that, but it's non-flexible. There's just one option. You set it to 1 or not, right? That's it. It doesn't visualize anything. You don't know exactly what it's doing. So from the top of my head, I don't know if it includes hyperthreads or not. So you know, it's good that we have it, but we need more. And why do we need flexibility? I work in a HPC center, and I know that lots of people run Julia on clusters, right? And this is just one example of systems that are just more complicated. They have a hierarchy to it, right? And you have to understand the hierarchy and address it if you want to write a performant code. So typically it's dual socket systems, so 2 CPUs and 1 compute node. And if you zoom in, right, you have a core in there, like there are many cores, of course. Within the core, you might have 2 SMT threads, like hyperthreads, right? Then they are grouped up on a die, right? 8 cores of them which share an L3 cache, and then you have a NUMA domain, like a memory domain. So there's lots of hierarchy to it, right? That you first have to understand, visualize, and then utilize with your pinning. How can you use threadpinning.jl to pin your threads? There are 3 different levels. The first one is like the physical level where you just specify pin to these cores, right? You just give the core ID and then there you go. Obviously, that's not the level that you typically want to work at, right? You want to work at a higher level. The logical level is there for you to specify in a logical way. I want to run, so in that case, 2 threads on the first 2 cores on the second socket, and then cores 4 to 5 on the first NUMA domain or something, right? It's an arbitrary example, but it gives you this logical abstraction for pinning threads. And lastly, we have this predefined stuff, which is good in most cases, where you just say pin to cores or pin to NUMA domains or whatever. There are also environmental variables and Julia preference options that you can use, but that's a detail. So how does it look? So this is the visualization. If you run thread info, you get this visualization. In this case, it's a 2 CPU socket system. There's no systematic distribution of Julia threads. They are overlapping, in fact. And then we can use, pin threads cores. Everything is pinned to cores. Pin to sockets. Now it's pinned to, in a round-robin fashion to different sockets. You can pin to NUMA domains. You can also visualize the NUMA domains. You can all do this interactively in the REPL, in a Jupyter notebook, whatever. Here's a little, benchmark. It's just an entirely memory-bound operation, just a DexPy. And in some cases, for example, when you run with 8 threads, just by changing the pinning, you get like an 8 times performance benefit because that system had 8 NUMA domains. There's more intricate things to talk about here, but this is a lightning talk, so I can't go into any details. In a real application, we saw something like 2.4 speed up. One thing I want to mention is thread pinning only pins threads to cores. It doesn't pin tasks to threads, right? Julia has task-based multi-threading. So in my example, I used at thread static to map that. But that's a discussion for another talk. So thread pinning only pins threads. We also have an option to just sort of respect external affinity masks. So if you're running under in a Slurm allocation, for example, which might already set the right affinities, you can just write pin threads affinity mask in your code, and it will in order, respect that affinity mask and do hopefully the right thing. And lastly, coming to an end, what I'm now planning to add, for the one MPI support, if you don't run in Slurm, like if you manually have not just one node but multiple nodes, you don't have to separate the threads. We want to add features for that. There's an issue open. We want to pin GT threads, right? In 1.10, we now have GT, the garbage collector threads. We want to control them as well. Windows support, as I said, there's an open PR for it, and I want you to help me out with it. First, I don't have a Windows machine. That hampers development a lot. I mean, what can I do? So if you care about Windows, reach out to me. Half of the work is already done. And obviously feel out to reach out to me, GitHub, here at JuliaCon, whatever other channel is out there. Thanks for the attention.
Thank you for the talk. Do we have questions? Yeah.
Very interesting. So when you make these decisions, you're combining your knowledge of both the task that is being performed and your knowledge of the nature of the hardware you're working with. What do you think the odds and obstacles are to starting to make these kinds of decisions automatically?
Yeah, that's a good point, right? I was talking to Valentin about the NUMA aware scheduler, right? That would like utilize so that you don't have to pin your task exactly, but it would realize, oh, you are using memory in a local way, right? How hard that would be or something, I don't know. But it's an interesting project, and I would love to work with someone on that. Like, it's exactly the direction I want to go, because currently I'm coming from the HPC background where you do the manual thing, right? You just say that thing has to run on core, whatever. But I would love to explore more the task-based nature of Julia, and again, like a NUMA-aware scheduler or these things, yeah.
But it's great to have the capability manually, so that then at least
yes, it's a first start. I don't know who was first.
How do you benefit if you pin the threads, but the tasks still sort of migrate thread to thread?
Yeah.
Do you still get the benefit of thread pinning? I was excited before I came here, but I'm
like the generic answer, maybe, right? I mean, the problem is how do they migrate, right? If they migrate within a NUMA domain, for the example that I made, right, the memory-bound one, you would still, be fine. But if they migrate like randomly across the cluster, no, you would have it wouldn't help you at all. Yeah. Well, Yeah, so that's the point, right? Like this, I think it connects to the question we just had, right? Eventually, it would be cool if there's an option that that the scheduler is aware of the hardware, at least some aspects of it. In that particular case, the memory structure, and then would migrate the threads in a limited way, right? Not just migrate them somewhere entirely else on a different socket, for example, but just migrate them within the NUMA domain or something. Yeah, but currently, as far as I know, it just does whatever it wants, right? So, yeah. So generically, you're screwed.
We have time for one last quick question. You?
I think Oliver had to, yeah.
So thinking about like using this in notebooks that I share with people and they might not be on Linux. Could we have it in a way that if you're on a non-supported OS, that it will not say, oh, this package can't be loaded here, but it will not do anything?
Great thing. I wanted to mention this on a different slide. So I have an option for package authors where you can put a pin thread statement in your package, but you want to have this force false flag because the user should be able to overwrite the pinning. Maybe they know better than you. But there currently the problem is exactly what you mentioned. Currently you can install it in an environment, so that works. But if you don't using, it will just complain. I want to change that, and it's super easy to change. I just haven't done it yet. Yeah.
We need to move to the next talk. Let's thank the speaker once again. So our next speaker is Venkatesh Prasad Bhatt. Apologies if I mispronounced it. And he will talk about shipping Julia packages with system images.
Hello everyone, I'm Venkatesh Prasad Bhatt with my co-presenter Joris Krak. We both ship our product Julia Sim at Julia Hub using system images. So we want to share our experience with why system images have been great for us, and also what can be done to get the best performance out of it, and also how do we ensure that it is always relocatable, or most of the time it is relocatable, and all features are also available. So system images have been very reliable for us. You can throw sort of 100, 200 packages and still it just builds. It might take an hour or so for installing all the artifacts and instantiating and everything and building. But once it is built, it is very readily shippable, and that makes it highly scalable. And then when on a target machine, when you just start it, it doesn't pre-compile again, so it can be used right out of the box and giving the speed. And the environment is consistent for entire team, and if there is an error or if there is same feature being worked on, everybody has the same set of features, so it is highly reproducible. And then if there are private packages, even code obfuscation can happen because you don't have to ship the source code, but that is pre-baked into the system image. So to make sure that system image works on the target machine, what all do we ship? First of all, system image. You can either swap out the default Julia system image, or you can also have a Julia file in user local bin, which targets the system image. And a lot of packages in Julia do need artifacts at the initialization, so bundle in the artifacts as well. And also provide the toml file. So project toml and manifest toml lets the user know what system, all the packages that are already in there and what he can use, and the features he can actually expect there. And then include the packages. So Julia needs to know that what modules are there. So if there is a private package, so the trick is remove all the source code and have an empty module script. So it just need to be that, and with that, system image will just take care of the functionalities. And then for the registry part, you can either, you can also add private registries, but at least add the general registry. Otherwise, package manager would install it the first time the system image is being used. And how do we go about building a system image that is mostly relocatable? So start with a dedicated depot whose target path matches the depot path should match the target machine. This avoids all the requires errors that you would get at the startup, which would also hurt the startup time. And then set the CPU target. This is the one that Julia binaries are built with for the x86 architecture. This covers most of the CPU targets there are. and then list out all the packages that you would need and you would expect your user to use with your package, and also try to cover all the primary dependencies of that so that it is more robust and you're covering most of the user base. And then this will allow, when the system image is started, you can import and use the package readily, but this does not guarantee that functions are, it doesn't precompile. So for that, you can pass a precompiled file. This can be just as simple as passing the run tests, the unit tests that are there, or you could also include a custom script which hits all the core functionality of your package. And then there are preferences. Toml sort of CUDA currently uses preferences to set the Julia CUDA version, and also ordinary DPQ and other packages have sort of toggles to decide what needs to be precompiled while the first time it is being precompiled. So for that, preferences Toml is useful. And always avoid hard-coded file paths. If there is a hard-coded file path, then it is guaranteed that it will not work. But then if it is unavoidable, then if the file size is small, you can use relocatable folders. If it is slightly larger, you can go with artifacts directly. And then lastly, if there are libraries that you cannot install on the target machine for some reason, then you can always find JLLs. So for most of the libraries, there are JLLs available, and you can find that they are versioned and they automatically install everything within the artifacts depot. You just have to add that to your library path. Yeah. That's all. Thank you.
Thank you for the nice talk. Are there any questions from the audience? Yeah, please.
Thank you for that. In your experience, what's the easiest or best way to approach that you kind of make sure that you include everything pre-compiled, because that can be really hard?
Yeah, so the thing is, you can add the unit tests. So they usually have the best coverage of the package already. So that ensures that everything that you would expect user to use is already pre-compiled and baked in.
So if I'm not 100% coverage, then I'm basically
for those particular functions, the first time it runs, that gets pre-compiled on the fly.
Everybody else can compile to it and not rely on tests coverage. It's also, it can get quite a thing, right? Because if you have to run the test, that basically means for us, for instance, we have to run the test of all of our dependencies, right? To get the pre-compilation working. So a lot of the times we even have to duplicate tests because they are very specific then to be running, they're used to be running in CI, that then doesn't work. So you have to, basically you're duplicating something, or you have to make them such a generic that you can't run them in a different repository as well to get these effects, which is, it's a lot of bookkeeping. So it's definitely something to control.
Any more questions from the audience?
So I heard a while ago that there might be some plans on really composable system images, because currently, like you want to build a thing and you have to, put everything into one thing, and if you maybe some part is more heavily developed than a different part, you still have to rebuild the entire thing anytime the most frequently updated package gets updated. So what are the sort of plans or timeline potentially on getting composable system images?
So system images are usually, if you already know that these package versions are well developed and you want to build on top of that, you can lock in. So this does lock in all the features, but if you want to be flexible and if you're developing, I think PKG images does the trick, and that's not something you can you would want to ship because it does not lock in and it gives the flexibility. But if you are developing, I think that just does the trick.
Yep. Any more questions? Okay. If there are no questions, let's thank the speaker once again. Our next and last speaker before lunch break is Stefan Sam. Let's welcome the speaker with a warm applause. And he will talk about the eStuff.gl maintainable type inference.
Okay, there we go. We're a bit earlier, but I think that's great. I prepared a talk for you today. We have actually 30 minutes. So this, the 10 minutes lightning sessions, they've been just previously, and now we have actually full 30-minute sessions. So yeah, a bit more relaxed. And we have time. I'm glad for every question which pops up. So I'm Stefan Sam. I founded Jolen.io. You see it also on the sponsorships. So that's me. And yeah, it's my baby. I'm really fond of spreading Julia within Central Europe, so Germany based. And this is actually not related so much to Jolen. It's really just one of the packages I wanted to have for a long time. And yeah, it took quite a while. You see. So we talk a bit about types today, and we talk a bit about traits. And this traits part is actually the one which motivated me. You're going to see. Okay, so let's start. So 3 parts for today. First, some teaser on type inference. So why is this actually an issue? Yeah, maintainable type inference. And yeah, second part, I want to give you kind of what ISDEF can offer you, just a quick summary, and then going to this motivating example of interfaces and traits. And last, because we have a bit of time, I also want to give you details about how this actually works. So and I think this is going to be a lot interesting because we are using some code rewrite. So this was actually my first package using the meta infrastructure of Julia in a bit more depth. Okay, so let's start. Julia's type inference. Yeah, you can kind of see it. So this is the motivating example. And I think can zoom a bit on. Yeah. So type inference in Julia is really not meant to be used by you. This is an implementation detail which is there to speed up your code. And there are some edge cases. And I was looking kind of for a really good tiny edge case which gives you the idea that this is magic. Yeah. And this one is nice. Yeah. So it's really super tiny. Very recently reported. So if you have a vector and a vector, then the standard base type inference method promote up is actually not knowing anything about this. Yeah, it's just returning the default type inference value, which is any. So might be a failure, might be something, might be anything. And yeah, and this just happens because it's not meant to be kind of used as an end user. It's really just meant to be used to improve your code. And yeah, so that's the issue. And these things, they may change actually from every minor Julia version to another, because yeah, that's really an implementation detail. This is actually not so much of a problem. Yeah, so usually no one uses this, or only a few persons, and actually no one should use it in a sense. But it's really not a problem because it's used to decide between compile time dispatch, if you want, or runtime dispatch. So from a semantic perspective, you're never facing it if you're really just using it for the standard use case of performance optimization. So yeah, the only case would be you want to optimize some performance. So yeah, you profile your code, you see, okay, here's some type inference is missing, and then you fix it. Yeah, you go somewhere around. So in this case, you would maybe use static arrays or something to improve the type inference. The official documentation actually makes this also very clear. There's not much documentation to be found on this, but the promote up actually has documentation. So this is really just a copy and paste of the standard Julia doc. And you see this little warning: due to its fragility, use of promote up should be avoided. It is preferable to paste the container element type on the type of the actual elements. Only in the absence of any elements, it may be unavoidable to call promote up. And even for empty, for the absence of any elements, it's still recommended actually to not use this because it's unstable and just might change from any version. Yeah, so I was hearing such responses when I tried to use the type inference system for my own cases, for traits namely, and it took really a couple of years until I came up with a bit more stable approach. So now I want to kind of show you the ISDEF package. So this is the very summary of it. Yeah? So you get kind of two little functions. The one is def, which gives the package the name. It just checks whether a given signature is defined. Not in the sense that you find kind of the method somewhere, yeah, which might just point to another method which does not exist for your types, but it's really type inference that works. So it checks whether this actually, yeah, has a proper type inference to some type, and yeah, not failing. And because this is type inference, there's also another function which I call out, capital, bless you. And yeah, and this is kind of the thing which is used behind the scene, which is really then just a wrapper around Julia's type inference. We're going to see a bit more details on it. For convenience, because in the traits application you always rather use values, yeah, or it's at least handy in Julia to just pass values around and don't care so much about all the type annotations. I have kind of these two versions, the one falling back to call the type of all arguments, and the difference is explicit, so if everything is a type, we just take them as types. If there's some value, we take everything as a type of everything. So it's always kind of a trade-off how you can, yeah, how to make things convenient and easy to understand and stable, and this is the trade-off. Okay, so let's take a look. So we have now our little example here, yeah, and if you use isdef, you practically have kind of one layer in between. So you can actually now fix this for yourself. Actually, I admit this should be a part of isdef itself. So if we want to fix space, yeah, it's good actually to not fix it in your own package, because then someone else might have another fix for it. So it's good to have a central place to fix it. And this would be naturally isdef itself. But as of now, it's currently not yet in the extra rules. I'm planning to add it. But still, it's a good example to visualize kind of how we would fix this. So if we use our out function here, just zooming in a bit, yeah. So we can just define this out syntax here. That's a special, this is kind of the method call under the hood, which everything else translates to you. You have this convenience functions on top. And here you see we expect a tuple type. Yeah, and the way in Julia we can dispatch on this is just specifying type, curly brackets, and then you have the full tuple type. This gives a little boilerplate, but it's really kind of from everything which I tried out with the less boilerplate. Yeah. So you then just type your function signature, all in types. And we can use kind of where syntax. We check kind of all these things. We have a vector and a vector and specify that our little t is a number. We can do all the stuff. It's just normal Julia dispatch, yeah, just now on the type level. And this is the mean which the package gives you mainly. Yeah, so this is the key reason why this is now getting maintainable. So if something changes, yeah, you can fix it. So maybe you have your rule right out of the box. So yeah, you can put it there, but just in case you see kind of from a minor version change to another, there's something breaking. This is now the way to control it. And yeah, and this works. So a little zoom in is not good enough for here, but even such an abstract dispatch rule is totally fine. So yeah, just does it. And yeah, and this infers also. So I haven't put the type inference over here, but so now if you apply Julia's type inference mechanism to this, this is really statically doing it. Of course, depends on your code, yeah. But yeah, so this what is statically inferable is statically inferred. Okay, so what's the time? Perfect. Okay. So now I want to introduce you kind of to my motivating application. So I mean, it's also already motivating to see kind of this breaking, yeah? And oh, if something breaks, you want to fix it, even if you don't know where to use it for. But this is now a real application. So I've been working with traits when I transition kind of from Python to Julia, because multiple inheritance is just not there in Julia. And if you would like to map it, then traits are kind of the most natural step to go for. So there's one motivating example for traits, and here I have kind of just a simple example using the standard interface in Julia, the iterator. Yeah, this is kind of Julia's default traits-like thing. And yeah, here's some example with iterator size and iterator element type. we just want to do it now on a single element vector or iterator. I call it single. And this would be, bless you, one example how you can use traits in Julia. So if you haven't seen this before, bear with me, it's kind of not so complicated as it looks. We really just have kind of multiple inheritance in the sense that we have a first function call, yeah, and then we get some extra type information from the given value. So we have this iterator element type or iterator size. They are real base functions, yeah, you can use them, and give them as extra input to a second function, dispatch, where we now dispatch on these extra information. So this is standard, Julia traits, do-it-yourself style, yeah. And this works well, yeah, this is kind of nice. And you can kind of then call the function and it works and you're sure, okay, my things are defined. And the way this works is, as you see, you have these helper functions, yeah. So this is the way current Julia uses traits. There's documentation on it. And yeah, so every of these traits, extra definitions, they usually represent one or two functions. Yeah, so you really define that you defined some functions. And of course, yeah, getting into Julia, I thought, man, yeah, this is real boilerplate. Yeah, so it would be nice if I don't have to write this, but it just now because I already defined the function. So this is the motivation, and as you can see, yeah, this is now solving it. Took a while, but yeah. So using the isDef traits, this is a bit how it looks like. And yeah, so we have, again, let me zoom in. We have again our little definition, yeah. And instead of having our extra, perfect, thank you so much. I got a little time update over here as well. We are not having extra definitions of these traits types which correspond directly to methods, but we now can just check them directly using our maintainable type inference. Yeah, and this looks still a bit ugly, so wait for the second part of this slide set. Yeah, so we have in Julia this val type, which gives us the possibility to dispatch on, let's say, bit values. Yeah, and it's a bit more complex, I think, than that. But yeah, just everything which you can imagine as bytes, you can dispatch on this. And we can now give us very similar two-function dispatch and get the same result. And now this is kind of safe and yeah, and maintainable, which it wasn't before. So yeah, it took me a couple of approaches. Yeah, and this is the reason why I wanted to have, why I wanted to have maintainable type inference. We can make this look much nicer. And because of this motivation, I actually already launched a package, some of you may know it, where traits, which gives you this unbelievable lovely syntax to do this nested function dispatch. Really, really concise, and for me this is kind of the preferred way to do the traits. So yeah, it does not enforce kind of some specific interface. Yeah, if you think of traits, this is always another motivator. Yeah, some don't focus kind of on this multiple inheritance in a Python super flexible dynamic style, but they rather focus on having a predefined set of functions which need to be defined, some IDE support or something. So just to clarify it up front, this is not doing it. Yeah? This is really just a nice syntax for this nested dispatch. No enforcement of kind of this function needs to be defined for your type or this function needs to be defined. It's really just making this nested function call simpler. Yeah, I'll zoom it in. Thank you so much. Yeah, well, that was a bit off. Okay, there we are. So this is the traits macro from where traits, and you see it's really envisioned, yeah, to work with something like isDef. Yeah, it's out there for a couple of years already. So you do it now really in one function definition, and you have an extended where syntax where you can put all these extra parts. And it has support for these standard Boolean return functions, yeah, these property functions, so because they are so common. And yeah, there is also support for other things, check out where trades, but in this case, this would be the syntax it now goes back to. A nice string of where trades is now that we can actually also overload this from other packages. Imagine kind of this nested function dispatch, yeah, it's just a side note. You can always overload the first one, yeah, but it's really tough to now get into the second from another package. And this is kind of one difficulty with trades, and this is taken care of if you use the where trades as well. So you can actually add further trades from other packages as well. Okay, so this is the motivating example, and yeah, the final syntax I'm using then to build my trade stuff. And yeah, and this is now safe to use. Okay, for the final time, I would like to go into some more implementation details. But first, I think it's a good time to pause. I think, yeah, this is really going to the implementation details. Are there some more questions for this part so far? Please, over there.
How do where trades interact with multiple dispatch?
So I think for the question was how where trades interact with multiple dispatch. So it's really just the very same as you saw doing it yourself. Yeah, this is a macro. It just rewrites the code to this nested function. And the way it kind of handles that you can overload it from somewhere else is that you, of course, need to use the trades macro itself. And it will just regenerate all the code. Yeah. So if you use the trades, it's kind of idempotent in the sense that it always generates the fully valid trades implementation and makes sure that all the line number annotations kind of point to the right things, and also makes sure that documentation kind of matches. But this is kind of the main trick. It just regenerates everything anew if you define kind of a new trades sub-implementation. Thank you for the question. Excellent. Please, another question over there.
Is it simple to use isDef to test whether a type conforms to an interface, like to verify that, like in a unit test?
Yeah, thank you for the question. The question is whether we can kind of use this type inference, especially isDef, to now check for an interface. Yeah, and I think, yes, sure. So you can use it to check whether it complies. The same like you would use it in this trades dispatch, yeah, there's kind of similarly. And I think this is also the Julia way to think of it, like you really want to have this testing. I think it's even better kind of if you have a real applied test, yeah, to check that the whole pipeline really works and not only the type level works of it. And by this you would kind of implicitly also get the type level. But I also like actually to put some check whether method error is thrown for something, yeah, in my testings. So I also like this type level stuff. So yeah. Great question, thank you. Okay, then going on to some implementation details. So heavy details. I have 4 things to go on. I hope time's. Yeah, I think we should have enough time. So main and most important part of this is actually code generation. Because yeah, you need to do some type inference, and there will be a time where you fall back to something clever than you, which is Julia's default type inference. But because it's so unstable, I was really looking for kind of a way to get the first steps right. Yeah. So kind of the simplest wrappers, yeah, that they don't need to fall back to Julia's type inference. This is where code generation comes in. So I take the part of your code and rewrite it. Inspection, we're going to look into inspection, how you can actually kind of get a bit more feeling what's actually going on under the hood. Like if you want to debug some of these things, that you really can easily look into it, what's going on. Val types is another special thing, because you, as mentioned, you have like this bytes types, which you can actually put into type level things, but they can also move around as normal values. So there's a bit of a combination. There's a special handling for this, and then also some notes on error handling. So let's go to code generation. I wanted to kind of summarize the rule which is implemented in the package. So it's, yeah, it sounds a bit more complex, but I think it's easy to get. So if the types are not all from Julia base core, so imagine we do this function call. Yeah, we have our signature. We check whether our element type function is defined for this or that. Yeah, and if all these things which come into isDef, yeah, are from Julia base core, and we have code generation supported, for this, then we use code generation actually. So yeah. So what's supported? We have args, keyword args, if else, plain statements and macros. We have not supported loops. So that's kind of key thing. Loops are actually quite hard to get code rewrite for it, and I just fall back to normal Julia inference. But still, it does for a lot of things. And here's one example to it. So having kind of this most complex thing which is supported. If you have just an if else method, yeah. That's a very simple implementation, but it has some branching under the hood if you compile this to intermediate representation. And now this actually supports this third case, which appears in types, which is kind of that you don't know. Yeah. So check this. We now use the val types I already mentioned. You have a special way to inject kind of these values into the type system, which is this val type of function. And yeah, and now we can kind of get really all three cases. And they are used also in the standard fallbacks, so you don't need to get this in detail on yourself, but it's good to see. And this kind of thing works just by code rewrite. This is not going back to Julia inference, but uses code rewrite to really do it statically. Okay, so inspection. So if you want to get more details kind of what is going on under the hood, this is really nicely refactored so you can inspect it. Take a look at the code. It's really, I think, easy to read and understand. And yeah, and we have kind of some further support. Actually, okay, dealing with the Zoom. So if we have a little tiny example, yeah, like such a wrapper, yeah, this is actually also a good motivating example why you need this. Yeah, you have a wrapper which does something on top of your normal function call, and if you now use has method, yeah, which would be kind of the naive approach to something like isDef, then you're already failing because this function is defined for everything. Yeah, so it doesn't give you any information about whether this function is really defined for your type in a useful manner. So we have a wrapper which wraps something totally arbitrary. I just made up with some types here. And we see our outer wrapper is working. Yeah, so it also everything infers. We have also support for the bits types. And we can now call code lowered, or using the IR tools package. It looks a bit more concise to me actually. The code IR. And you see, if you use the tuple signature type, yeah, so this is the real machinery under the hood, yeah. If you use this one, and you can inspect kind of what code is generated, and it's really built in such a way that you can now read it. So this is going into the wrapper, yeah, and yeah, so you see that this apply iterate, which is kind of using the dots, yeah, the splash one. This is now really wrapped. Okay, 4 minutes left, so let's get there. Okay, so we have also an out debug, which is now doing the things iteratively. As you've seen before, okay, we only had this first layer, yeah. So if you really want to understand what's going on, man, so how do I get in the next layer? And out debug is just for this. So here we can really see all the different layers. So some extra information, then it goes deep into it until it really returns, and you have all the details. This again using IR tools magic to rewrite your code and add this extra debugging outputs. So that's really handy, and yeah, was handy for developing, but I guess also helpful for understanding what's going on, so that this is really transparent, which is a great important part of maintainability. Okay, only a few times left. So val types, just to mention it, there's a special val type of, which is kind of a function which just wraps these types extra, and it's used internally as well to kind of improve the inference part, because if you use just literal values in your code, yeah, we can use them for type inference. They are not dynamically, they are static, we can use them. And yeah, and you also need to define them yourself. If you make this definitions yourself, yeah, check that if you have kind of some val type like bool, you also need to account for the case that it's a val type. That's kind of the downside of it, 2 different cases, if you have a literal value or not. We have also some helper values for some helper methods for this, like a signature without val types function to help you along getting rid of this extra performance improvement. Okay, some information about errors. I think I'm going to skip this to get more time for discussion. Yeah, so we have there's extra error handling in it. Yeah, going back if you have more time. So let me summarize. So what you see today is def, which therefore maintainable type inference. You've seen kind of one motivating example. The minus of a vector and a vector with a number is really not working out in current Julia. And we can easily fix this if we have some maintainable layer on top of it of standard type inference. So usually you're actually not motivated to use this at all. Yeah. So if you have used it, you're probably some niche Julia user, but now you can actually use this safely. And one motivating example to use this kind of in the mass is really this traits case. Yeah. So there, you yourself may want to use type inference to get rid of the boilerplate. Okay, we've seen some implementation details. So you have code generation, which does good for kind of a couple of standard cases, but it falls back to standard Julia inference. It will warn you in case it's just unsure. This is not a good idea to go back to standard Julia, but it still does. We have some support for byte types to get better inference, and we have kind of also some further error handling so that you have a good feedback when it's going to get unsafe. Okay, that was a lot. I want to have a few seconds, like to mention. Check out cloud.jolin.io, recent thing of this company, deployment of Pluto. You may love it, and I'm really looking for testers. So yeah, check it out. And meant for companies in the end, so to use Pluto, and may also be something for you. Reactive notebooks, I want to spread them in Germany and Central Europe, and yeah, if not also to you, that would be great. Okay, so then thank you very much for being with me for this talk. I have a couple of open questions we can also discuss further. You can reach me anywhere, so get my contact details, scan this nice QR code, and yeah, I'm happy to get more questions. Thank you so much.
Thank you for the talk. Are there any questions? Yeah.
Yeah, please.
You talked about the difficulty of handling loops. Can you handle recursive function calls? Do you handle a nested function?
Nested function calls. That's a good one. I think this didn't pop up because so this package is working on intermediate representation. And you find loops in intermediate representation in the sense of jumps, which are kind of recursive. But I guess nested function calls just don't pop up on this level. So yeah, never encountered. Yeah.
So if I wrote instead of a loop, say a tail recursive function, would that make it easier, or I don't know a ton about that.
Yeah, not sure. No, it's really tough to get into this really detailed. So we would have to look into more details offline, I think. So because this intermediate representation is a different way of thinking about Julia, and yeah. But thanks, cool question. Yeah.
We have other questions?
Question, I think you have question over here.
Thanks a lot for the talk. So actually, this is something that we need in Jump. In mutable arithmetic, we always need to do this. And currently what we are doing is that we need to hard-code the promote operation method for every type we have. And if it's not hard-coded, we default by coding the operation on 0 of the types. Which doesn't work, for example, if it's a division.
Yeah.
Then it's 1 and so this is quite interesting. And something I don't quite understand is why if what you're doing is better than call the compiler that return type, why is this called and compiler that return type not doing this?
Yeah, so there was some application for this. That's nice. I'm looking forward. Let's sync. And the question kind of core compiler.return type, which is the main machinery. That's kind of the core function. I mentioned promote op, and core.compiler.return type is another interface to this. And it has the same difficulty as upfront. So, I mean, you can kind of also overload this, yeah, but it's not intended to. Yeah, this is really kind of an implementation detail which you should never specialize for some own types.
What I mean is that basically return time in your package are solving the same problem. So what are the essential difference between your approach and their approach? Why do they support for loops and you don't? And why are you more accurate than them?
That's really, I think it's different. So the normal standard Julia type inference is really to make this decision: can I compile this up front, or do I need to make a runtime dispatch? And this is kind of completely different target. Yeah, they just want to make this balance between not too much time for compiling, but still really lovely runtime performance. And this is just a different goal. And this is now really to use it on an end user, and not to decide between compile time or runtime, but real user-facing interface for type inference.
So return time try to stay very quick and doesn't care about runtime not making the inference correctly, and you really want to give when it takes time to arrive to conclusion.
That would be one way, yeah, to put it. But yeah, yeah. Okay, thank you so much.
We have time for one last question.
So there have been a couple of mentions over there. I think the first one, please.
Yeah. So kind of a basic question, but are you building? Are you like taking the Julia's internal type inference and patching on top of it cases to catch stuff and to fix regressions, or are you building like an entirely separate system?
Thank you very much for this clarifying question. It's about kind of whether this package is built on top of Julia's default type inference, or whether it's completely separate. And yeah, I'm sorry to not have made this very clear. It's really built on top. So it falls back to Julia's default type inference, because this is just so handy for usage. Yeah, building this on for yourself is not feasible, and I wouldn't want to do this. It's really kind of, it has a couple of cases, like mentioned, like the simple cases, if else is like the most complex, where it really falls back to custom code generation. So everything is static and inspectable by you. Yeah, this is like fully transparent. But in case this doesn't work out, it falls back to Julia's type inference. Yeah, and of course you can also always define your own dispatches. Yeah, that's also kind of this layer that's code generation and the possibility for you to specialize it or fix it in the sense, yeah, for your cases. Yeah, thank you. Awesome question.
Yep, thank you. So it's time to move to the lunch break. So let's thank the speaker once again with an applause.
Thank you very much.
Check, check. Check, 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 check.
All right, is this the mic that we have?
That's extra.
Oh, okay.
And mic buttons.
Ah, hi. Hey, I'm Jeff. I'm Chair of the Secretary. Oh, we got it. That's all we do. Great.
Do we need to do an audio check? Is that?
No, Jeff, if you don't have this microphone, you leave it the chair.
I'm the chair, yeah.
Yeah, I'm just going to watch the shop.
Yeah.
And then it lights up right there.
Okay. So this is me speaking normally. Are we coming through all right? Okay. More people have been to Berlin than I have. A lot of other semantically void but syntactically correct sentences, can I say? Okay, we're good, great.
My friends have more friends than I have. Semantically correct sentence where you say buffalo like 8 times in a row.
Yes. Yep. Or Wiersdorf, whatever's easiest, but Wiersdorf is the traditional German way.
All right, testing seems to work. Good. Okay. We will start in 5 minutes.
it just also, for me, and you guys are using variable, like scientists need to like, it needs to be some, I don't know how to use it. Like, I'm interested.
Well,
as an
it
inspiration.
could replace things, but I actually yes. Not good enough.
I want to fix it. There's some stuff that needs to change.
Yes. I remember the finals.
Okay, welcome everyone. It is 2 o'clock, so we're going to start. I am Jeff Pizanson. I am chairing this session, the best session. So our first speaker is Ashton Viersdorf. He's a PhD student at the University of Utah, and he's going to be talking about topics I think near and dear to all of us, IEEE floating point and errors. So please.
Thank you. Yeah, I'm Ashton Viersdorf, and my colleagues and I at the University of Utah have developed some tools to help you track down problems in your floating point code. And our tool set, called FlowFPX, has already proven useful. So we hope that you, too, will find it useful. Imagine that you're a busy scientist doing some numerical work. Now, for some of you, you won't have to imagine that. That's your reality. But for the rest of us, let's all imagine that you're working on doing a heat simulation where you're observing the change in temperature in a slab of metal over time as seen as that animation. All's going well, and you're tweaking some parameters, and then all of a sudden your simulation starts looking a little unhappy. Ah, man. What happened? Where did that hole come from? Well, the answer is NaN happened. What is NaN? NaN stands for not a number, and it's part of the IEEE 754 floating point spec. What is this spec? Well, IEEE 754 standardizes floating point representation and operations across architectures, so it saves us from the pain of having to port every little floating point function that we have to new hardware. And we can rely on some consistent behaviors across all of our platforms. This spec also describes some things called exceptional values, of which NaN is one. What are those? Well, first we need to remember that floating point numbers are a discrete and finite approximation of real numbers. Compared to the continuous real number line, floating point numbers are discrete points along this region. And there's always some gap between the real values that we want and the values that we can represent in floating point. And that gap is error, and that error accumulates throughout your computation. And error, combined with finite representation, means that you get into some crazy situations where we get exceptional values. William Kahan says, an arithmetic exception arises when there is no result that would be acceptable universally. So let's look at what the exceptional values are that we have. There's NaN, what we've seen before, not a number. There's infinity, which is what we get when we exceed our representation capacity, and subnormal values when we underflow. In this talk, though, we're going to be focusing on inf and NaN. Let's drill into NaN. NaN arises when there's no clear mathematical answer to your computation, something nonsensical like dividing 0 by 0, or there are some other ways other than these listed here, like taking the square root or logarithm of a negative number. And once a NaN appears, a NaN will propagate, meaning doing some operation with a NaN will result in a NaN. Like if I have 5 and I add it to NaN, I get a NaN out. I don't get NaN 5. So you might be wondering, why don't we just throw an error in these situations where it doesn't make sense? Well, as Kahan said, that's not necessarily the thing you want to do in every situation. So you need to use code that's tailored to your needs, but properly crafted code isn't always available, right? So hence we have exceptional values that flow through code with a lifetime that we've characterized as follows. In the beginning, we have gens, what we call gens or generations, when an exceptional value comes into being. Once once an exceptional value has manifested, then the next phase of its life cycle is called a prop, or a propagation, where that value proceeds through operations, hopefully manifesting in the output like that hole that we saw earlier. And that's nice because we know that something's gone wrong, and we now have a clue that we should go back and try and figure out, find a problem and fix it. But there is one more phase of its life cycle that can occasionally crop up. And instead of manifesting as, say, a hole in a graph or a blob of white on your chart, there are kills, and that is when an exceptional value silently gets swallowed by an operation. Instead of letting us know, it can silently lead our computation down the wrong path. So kills are very risky because our computation can be wrong, and we might not even know it. We'll see an example of when that happens shortly. So let's go back to our graph. So you've got a problem. You've got this hole in your graph. You know something's wrong with the computation. So down the rabbit hole into the bowels of your code. You want to find out where that NaN came from. So you start going through all your source code and going over all your equations with a magnifying glass. But you know that doing this is going to be a lot of work. You're going to have to put like print statements everywhere or some other kind of profiling, and that's going to take a lot of time to do, and then that's going to generate a huge log file that you're going to have to comb through, and that's not fun. And you're just like, this is awful. Like, I don't want to do this. I want to get to my work. I don't want to have to deal with this crummy floating point stuff. And you wouldn't be alone if that's how you feel. We found hundreds of issues in Julia repositories on GitHub that mentioned NaN somewhere in their description. So this is not like you're not alone. It's okay. Other people are suffering with you too. But fortunately, our FlowFPX toolkit comes to the rescue. FlowFPX can save you from that manual work. But you don't have to take our word for it. The folks who have been working on the RxInfer package found themselves in this situation. RxInfer is a Bayesian network inference library. And in issue number 116 on the repository, they said, they had a problem, and they said, it is impossible to trace back the origin of the very first NaN without performing a lot of manual work. This limits the ability to debug the code and prevent those NaNs in the first place. Sound relatable? Well, we introduced them to FlowFPX's float tracker tool, and the next day they sent us a message. So I'd like to point out that we never saw any of their code, but they were able to find the NaN on their own. So if you are a busy scientist, please go and try our tool. It works for people other than its creators. So onto our tool set, FlowFPX. FlowFPX can help you solve these problems of tracking down exceptional values, but we also provide tools to help you harden your code so that you're less vulnerable to when those exceptional values can crop up. We use a variety of different technologies to make this work. We lean heavily on Julia's type-based dispatch. We do some fuzzing, and we have stat graphs, and we also do a little bit of flow graph diffing. More on all this later. There are two main components to FlowFPX right now that we'll talk about today. There's Float Tracker and Coalesced Stack Trace Graphs, or CSTG. Float Tracker uses Julia's types and overloading to produce stack traces and fuzz programs from the inside out. And CSTG takes the stack traces that Float Tracker produces, and it can coalesce and diff those stack traces. Now, CSTG is a standalone tool, but it works really well in conjunction with Float Tracker. Excuse me. And we'll be focusing on Float Tracker for this talk, as it's written in Julia for Julia programs. And we are at JuliaCon after all. But we'll see a little bit of how CSTG can help us out. And this is a growing tool set, so more in this vein later. Let's take a look at an example. This example was inspired by Edelman et al. There at the archive link. Let's write a function to compute the maximum of a list. We take a list in, we keep track of the biggest seen value, and then we iterate through that list. And for every value x in that list, if it is not less than the maxine value, then we swap out the maxine value for that element that we're looking at. And then we'll print out the result. Now, spoiler alert, this nan in our input list is going to make life interesting. So let's see what happens. Let's go ahead and run this code, and just for sanity's sake, what are we expecting? That's right, it's the number 5. So let's go ahead and fire this off. What? Wait, that's not the maximum value of the list. What happened? Well, we could go back and like try and figure this out manually the way we're used to, but let's call float tracker and ask for some help. So the first step to using float tracker is to say using float tracker. And then you wrap the input in our tracked float 32 type. And float tracker builds up logs and it flushes them periodically to file, but just at the end, just to be safe, let's just ask float tracker to finish up tidying those logs. Okay, so with these few modifications, we rerun our code, get the same result, but this time we get some log files. We get 3 log files, one for each kind of event in an exceptional values lifetime. As a refresher, this is how we categorize those events. If there's no nan in the arguments, but a nan in the output, then that's a gen because a nan's been brought forth into being, and so that event gets logged in the gen file, and so on with props. Nan flows in, nan flows out, and a kill, nan flows in, but no nan flows out. And when we run this, you'll notice that we get some kill logs, and that should always send up a little bit of a red flag. It's like, maybe there's something going on there. So let's take a look at the kill logs, and this is what we see. The kill logs give us, well, all the logs actually, but they give us a stack trace of where that event happened. And the kill logs give us a stack trace of where a nan was killed. And it looks like the less than function is the culprit here. And the arguments are nan and 4. This is a kill, of course, because a nan goes into the comparison, but it doesn't come out. The thing is, that works both ways. It doesn't matter which way you compare against a nan, you always get false. That's part of the spec, by the way. With those clues from float tracker in mind, let's step through this carefully. So 1 is going to be our first max scene value. And then we move on to 5. We compare with the max scene, and 5 is not less than 1. So we swap. And 5 is now our max scene. Next, we move on to 4. 4 is less than 5, so we don't swap. And now something interesting when it comes to nan. Because we're comparing against a nan, nan is not less than 5, and so we swap the max scene for a nan. And then when we move on to the next value with 4, 4 is also not less than nan, so we swap that out for 4. So there's our error right there. That's what happened. Now, the correct thing to do in a situation like this would be to propagate or otherwise guard against that nan. That depends on your situation. But the nice thing is float tracker has given us clues as to where to look. So as a recap, to use float tracker, you simply require float tracker, wrap your inputs with tracked float types, and then flush any buffered logs that haven't been flushed to file already. Let's take a look at another example. There's this library called Shallow Waters by Milan Kluver, who happens to be giving a presentation, I think, in that room over there right now on climate modeling. So thanks, Milan. Shallow Waters is a Julia library that lets you take a mesh of a sea floor and then run a time series simulation to get the speed of currents in the water over that sea floor. And like many simulations, Shallow Waters operates by modeling one time frame after another. And there's a parameter called the CFL parameter that controls how fast information propagates through a time series simulation. Small CFL values give you accurate simulations, but slower renders. And big CFL values give you faster renders, but you run the risk of getting some instability into your simulation. And what does instability look like? Well, here's an example of some shallow waters output with a modest CFL parameter. But if you dial up the CFL parameter a little too high, you get something that looks like that. And, all that white is where NaN has crept into the computation and come out into the output as a whole. So let's say we're at this situation here, and let's call float tracker to see if we can figure out where those NANs are coming from. And in this case, we want to try and drill down to concrete values as fast as we can, and to hand that off to a domain expert to figure out how to fix our simulation. So just like before, we run float tracker and we get log files for every different kind of event. And this time, because we're trying to figure out where those NANs came from, we're going to take a look at the gen logs. And this file comes in at the petite weight of 3.1 megabytes. That is a lot of logs to sift through. Fortunately, FlowFPX has another tool called CSTG to help us out with this. So what CSTG does is it summarizes flows or groups of stack traces for us, exactly what float tracker produces. And this builds off of some of the work of STAT from the Lawrence Livermore National Laboratory. So what does CSTG do? Well, suppose I have a file full of stack traces like that. Here I have 5 stack traces with 4 frames each. CSTG draws a graph, one node for every frame, and then as it proceeds through the groups of stack traces, it adds or increments an edge between nodes for every pair of consecutive stack frames. So this gives you a glanceable view of what the most heavily trodden areas in your code are, though the thin areas are still worth investigating. So we run CSTG on our gen logs, and we get something that looks like this. It summarizes all those megabytes into a nice little graph where the thick arrows and high numbers mean that those frames showed up next to each other quite a bit. So, and we read these graphs from bottom up. We see that down there in the bottom right that most of the problems came from that addition inside of the continuity itself. So let's go into that log file, but now we know what we're looking for. We don't have to try and comb through all those logs and make sense of it ourselves. So we pop open that file, and here's what we see. Okay, so there's a NAND gen, and it looks like the arguments to addition are infinity and negative infinity right there. And that is one of the nonsensical computations that is known to yield a NAN. But that begs the question, of course, where did that infinity come from? Well, we can call float tracker again and get some help with this. So here is the CSTG for the infinity gens. And it looks like almost all of the infinity gens are coming from this exponent. So let's go ahead and look at the logs. And here's what we got. So I'm going to pull out the salient values again. Negative 1.5 times 10 to the 31st squared. Okay, that is definitely going to blow your 32-bit representation out of the shallow water. And now we're out of exception land. Woohoo! So we've got concrete values that we can hand off to a domain expert now. Float Tracker gave us all these nice logs, and with CSTG, we were able to summarize them very nicely into a glanceable view to help us figure out where those problems were coming from. Now you might wonder, okay, cool. So I've got this summary of where of what like the heavily trodden areas of my code are, but how does that flow change over time? Because you might have one little thing that goes wrong at the beginning of your execution, and then your code just kind of spirals out of control for who knows how many iterations. So what we can do is we took our CSTG gen logs and we just cut them at the 10% mark into 2 files, part 1 for the first 10% of the execution, and then part 2 for the last 90% of the execution. And then we generated the CSTGs for both of these. And we could look at them and compare to see what's different, but that can be a little hard to read, and if your CSDGs get big, that gets unwieldy fast. But CSDG gives us the ability to diff graphs. And so we diffed those two graphs that you just saw, and this is what we get. Those green arrows are flows that are new in the latter 90% of the execution, and the red flows are the red arrows are flows that were present in the first 10%, but not in the latter 90%. This is just another clue to help you determine what's going on inside of your code. Let's talk a little bit about fuzzing now. Why might you want to fuzz your floating point code? Well, here's a video of a robot Formula One car crashing straight into a wall. What happened? Well, what happened was that a NAN got sent from a faulty sensor sent a NAN over the sensor bus. And the code for the steering column didn't know how to handle that. It picked it up, it just saw it come across the bus and was like, oh, I'm going to go into my default state. And its default state happened to be a hard turn to the right. And so when the command to go goes to the motor, it's like, okay, I can go now, but the steering column's like, I still don't know what I'm supposed to do, so I'm going to stay hard turn to the right, and boom, right into the wall. So, you know, if NAN doesn't show up in testing, we might wonder, how can we be confident that our code won't crash, sometimes literally, in production when a NAN might actually show up? So let's call Float Tracker again and ask for some help. So we started fuzzing this library called N-Body Simulator, and it does an N-body simulation of massive bodies. And we turned the fuzzer on, and we got nothing, like zilch. There were no floating point operations anywhere in this code. It turns out that N-Body Simulator offloaded all of the heavy work onto the ordinary diffeq library, and that's where all the math actually happens. So we said, no problem, and we'll expand our scope to the ordinary diffeq library. So here's how we configure our fuzzer. Every time you do a floating point operation, you roll a two-sided die, also known as a coin. And if you crit fail, you inject the NAN. But we only do this inside of the N-Body Simulator or ordinary diffeq libraries. I don't want to really fuzz the standard library. I'm not interested in that right now. And then we save that fuzzing run to an injection file. This is the full set of operations that you can use to configure your fuzzer. You can control how many NANs you inject if you just want to murder your code with NANs. You can do that. We just default to 1. And then we also give you a little bit more fine-grained control over where and when you inject NANs. So with this injection recording, fuzzing includes some randomness, and recording that fuzz session lets us replay that fuzzing session as many times as we'd like to inspect an interesting occurrence, or we can repeat those injections after we harden our code to make sure that they've actually done something. So we ran our fuzzer, and we got we noticed that the program said, notice some instability, I'm going to stop now. But it didn't stop. It went to an infinite loop. We're like, huh, interesting. And we also saw some kill logs come up, and we're like, very interesting. And so we looked at the kill logs, and we noticed here that there was something inside of this solve.jl file. So let's go and look at that right now. Here's a smoking gun as to where our bug came from. There are two while loops in this function. The first is this big while loop that iterates until the tstops list is empty. And then there's this inner loop that on every iteration it's supposed to pop something off of that tstops list. But it turns out that this tdir variable right here was NaN. And as we saw before, any comparison with the NaN is false. And so this inner loop never ran. Consequently, the outer loop never stopped because nothing ever got pulled off of the tstops list. So we found a vulnerable place, and you can see our bug report here on GitHub if you so desire. Let's get down to the nitty-gritty of how we did this. Did we manage did we write a custom Julia kernel? No, we actually did this all entirely inside of userland, thanks to Julia's magic. Our first step was to take all of Julia's floating point types and create our own tracked float wrapper around that. A tracked float is a subtype of an abstract tracked float, which is a subtype of an abstract float. So anywhere where you can use a float, our tracked float is an acceptable thing to stuff in there. With these types in hand, we overloaded all the operators, and here's an example of how we overloaded addition for the tracked float 32 type. We just unwrap both of the track floats, add them, check to see if there was anything interesting that happened, and log if something interesting did happen, and then return the result wrapped in a new track float 32. So we're making heavy use of the magic of Julia's type dispatch to make this work. Of course, this would be pretty hard to maintain if we did this by hand, right? There are 3 different track float types, and there are dozens and dozens of operators in base, and like, who would want to do that? Do you have a question?
Yeah. Why is the track float a
Parametric type?
I think you could make track float T, where T is a number, and then you could track arbitrarily, like abstract floats.
That's a good question. Can we take it offline? Yeah. Thank you. Thank you. So yeah, you might be wondering, like, how do we make this all work? Or like, that's a lot of code to write, but fortunately, Julia also has macros. So this approach was inspired by Milan Kluver's Sherlock's library. Thanks again, Milan. Well, we essentially just have 2 big for loops. We have an outer one that loops through each of our types, and then for each of the types, we loop through all of the operators, like plus, subtraction, division, etc. Our code works out to be about 218 lines of code, and that's like not counting that's including white space and comments, so this isn't like a massage number or anything. This is like the length of our file. And that generates about 645 function variants. Without the macros, we would have ended up writing about 4 lines per function or 8,000 lines of code, so this is over a 10x reduction in code size. So thank you, macros. Another nice thing is you can write your own overrides too. This is something we encountered with some frequency. There'd be some fancy function somewhere that would dispatch directly on a float 16 or a float 32 or some brand new type that was specific to that library. And you can write your own overrides whenever you want to work with a track float type. So here's an example from one project that uses this special 4-diff dual type. Without modifying Float Tracker or the library of interest, we were able to extend Float Tracker to support the library's custom data type. So type dispatch is really awesome and really powerful. In conclusion, I hope you remember that tracking down instances of NaN and infinity does not have to be painful. Float Tracker does it all for you automatically. Float Tracker and CSTG are also ready for you to use. You can find them wherever fine software can be downloaded. By that, I mean like GitHub and JuliaHub. We had a lot of fun making this work with Julia's type dispatch. It's a powerful paradigm. But the most important thing that I hope you remember is if there's something strange in your floating point, who are you going to call? Float Tracker. Thank you.
All right, thank you very much. You know you've done a good job with the finish of the talk if I don't have to ask people to applaud, but they just do spontaneously. We have time for a couple of questions. You can call on people, and I will repeat the question.
Very good question. Can I ask Float Tracker to track a separate value that isn't NaN float? So if I have some code running, then I know if it crosses like 10 to the 16th or something, that's already bad enough. Could I ask it to, instead of tracking NaN or inf, to track the separate value?
All right, so the question is, can you track something other than NaN or inf? Like if you're interested in values crossing a certain specified threshold, for example.
We don't have a way to easily do that right now, but it's not hard to extend that. And so maybe if that's a concern that lots of people have, then we'll make that. When I came onto the project, it was just NaN, and I added an inf in like a day. So there's no technical reason why we couldn't do that.
And I have a question, which is, can you comment on the overhead of this? Like if you're running something like shallow water, what's the slowdown?
Yeah, let's see. I actually have numbers for that exact thing. So it's big. So if you run shallow waters without a NaN, it runs in about 3 seconds. If it gets a NaN, it aborts in less than a second. If you turn on Float Tracker and get a NaN, it's like It runs for over a minute. It's like a 9,000 times slowdown. Most of that overhead comes from asking Julia for its stack traces. And it does that as late in the game as possible. So if you filter the event types and limit the number of events logged, then you can really cut that down. So like if we just say, hey, float tracker, only log the first 100 gen events, for example, then the overhead goes way, way down. For overhead, running Valgrind gives you about a 100 times slowdown. So just remember, this is not a production tool. Like, it's a profiler. You don't run this on your production code, but it's not so prohibitive that it's infeasible. It works and it's practical.
Yeah, I was thinking that the feature of being able to specify in what packages you're interested in was going to be the slow one, because you have to look at the stack trace every time, right, to do that? Yeah, sorry about that.
Yeah. That's only on fuzzing, though. So
one more quick question, maybe?
Yeah, okay.
So what happens if my program is like a bunch of Julia and Mark's code, and then I call into a black box C solver, and then I do a bunch of other Julia code? Is this package able to kind of manage that?
Yeah, the question is, what if there is a black box C library in the call chain somewhere?
That's a good question. Well, yeah, like calling a GPU. So FlowFPX does have some tools to help with some situations around that. I don't know exactly. We can talk more offline if you're interested, and I'm sure there's a way. Where there's a will, there's a way. Okay.
All right, yeah, one more quick question.
Okay. Yeah.
Really quick.
Yeah, the point by understand we can track it then.
Yeah, can flow tracker can track the land not in the Julia code, but other code in the shared library, like the using the C code and functions in the shared library. If the land is happening, that can
same question, basically non-Julia code. Yeah, in the call chain. I think same question basically. Yeah.
No, its focuses on nans coming from Julia code, but you would be able to see that nan pop up. You would get some trace of where it's coming from still. Like, you'd be able to watch its propagation. So.
Would it be possible to note if you've got a tract? Like, would the propagations be tracked?
Yes, you can turn that on. It's fairly expensive, and so by default they're off. But yes, that is something that we do track. There's the gens, props, and kills.
And the props would be tracked even if it came from a black box C code?
Yes, yeah. It would have to run into another track. There are technical details, but the short of it is yes, we can find a way to make that happen. So.
All right, we've got to move to the next talk.
Okay.
Which is Lilith. Thank you again.
Oh, you probably need this mic.
All right, I will do an introduction while we're getting set up here. So the next speaker is Lilith Hafner, talking about sorting. So Lilith is a prolific Julia contributor, to say the least. Lilith is a very frequent contributor to the bi-weekly triage calls that we hold, and has done a huge amount of work on sorting. And I'm really looking forward to this. This should be very interesting. I believe we have some of the coolest sorting libraries out there right now in our standard library, thanks to this next speaker. So please take it away.
About sorting. That's base.sort.sort. There's something, yeah? Oh, not on. Oh, it's on the off side. Oh, lovely, lovely. Is this on now? Okay, so what are we going for with sorting? This is like if you're sorting a vector. If you've got like 732 and you want 237, you call sort on it. The main goal here is for it to be easy to use. You just, most of the time you want to sort something, you just want it in order, and it's not performance critical, and you just want it to work. And that is priority number one. Priority number 2 is high performance. Let's make it fast whenever possible. And in many cases, we can get it really fast. Although, just a note, if sorting is your bottleneck, you're probably doing something very wrong. But if that's the case, then Julia is a good language for that. Anyway, some other things we want for sorting is for it to be extensible and customizable. So you should be able to sort any sort of element if you provide a way of comparing them. And even more optimizations for elements. If you have a package that defines certain structures or data types, whether it's a collection or an element type, then you want it to be able to be more efficient. It should be extensible. So there's actually a lot of things that we can do with sorting. The domain space for this design is pretty broad. We want to support custom container types. We want to support higher dimensional containers. That's like a matrix or just like an n-dimensional array, which will sort each slice as opposed to sorting the slices. Anyway, we want to get sort perm as well, which is getting a permutation that will put your data in order. So if you have a data frame and you want to sort it according to the first column, you might want to get the permutation that would put the first column in order and then apply that permutation to all the columns of your data frame. So in general, sort perm is something that we provide, as well as partial sort. You can sort a vector, and you can sort a view of a vector, which will just take a little section and put that section in the correct order. A partial sort is slightly different. If you, say, have a vector and you want the top 10%, you want to find them and sort them and put them in the right place, that's what partial sort does. So it sources data from the whole vector and just places them correctly for part of it. We also want to support custom ordering. So you can put things in reverse order. You can sort it by a certain function that's applied to the elements before comparing. So if you have a bunch of people and you have a field height, you can sort by height, and that will give you arrange people by whatever the function provides. Sometimes that's not possible, and you want to provide an arbitrary comparison function, and that's also supported. But there's some considerations for performance. This isn't a but. And there are some considerations for performance and for some other factors that we need to think about when making these systems. Oh, this is starting to give a little bit of feedback. So known types and orders. If we have some common case that's well known, we should be able to have really good optimizations. So if we're sorting IEEE floating point values into ascending order, that's something that's well known and we should have a good, efficient algorithm for, and we do. Patterned input order is another thing we want to take into account if it's partially sorted already. We don't do a great job of taking that into account. If it's fully sorted, we do, or if it's reverse sorted, or several other special cases. But in general, patterns can be taken advantage of, and that's a weakness of the current system. Input size, we want to be able to support different input sizes. A small input should have a simpler algorithm, whereas a large input might warrant a more complex algorithm. It varies based on the machine specs, and those are all for performance. And then stability is another consideration we want to think about. And this is, I'm listing all these things to kind of justify why sorting could be complicated, because there's like more to it than originally it seems like. So stability is if two elements compare equivalently. That is, one is not less than the other, and the other is not less than the one. You don't rearrange them. And so if we are comparing people by age, and two people are the same age, we don't want to swap them if it's stable. If it's an unstable algorithm, we're allowed to swap them. And so some domains require stable algorithms, and some do not. And then, of course, there's extensibility and backwards compatibility. If someone's done something before, we want to keep allowing it in the future. So there's a lot of optimizations we use. I'll get into these later. But first, just want to give like a higher level picture of what this call stack looks like. When when you call a sorting function, whether that's partial sort, whether that's sort, whether it's sort bang, whether it's partial sort perm bang, whatever it is, and whatever input types, it gets reduced to sort bang and sorting an abstract vector. So if you want to sort an array that's multidimensional, we sort a bunch of vectors. It gets reduced to that. If you want the sorting permutation, the permutation that will put something in order, then we sort an array of indices, and we give a custom ordering, where we say an index is less than another index if the values, when you look it up in the data, are less. And for like an iterator, we'll collect the iterator and then sort the collected result. And all of this then gets passed to this underscore sort bang function, which is new in Julia 1.9, I think. And that is an internal function so that we can be very clear that it's subject to change, and it does all the magic, and it has all the optimizations, and it's internal because we want to be able to change those optimizations, and even the design of underscore sort bang. So how does underscore sort bang work? That's like how this becomes fast, how we have a system where we can fit in more optimizations after the fact, how packages, if they're willing to muck with internals, can fit in optimizations. It looks kind of like this. There's a bunch of methods for underscore sort bang, and they're dispatched based on the algorithm. So the algorithms are nested, like this would be how you would call it. So check pre-sorted is an algorithm, and when you call sort bang with that algorithm, it will dispatch to that first method that's listed, because the algorithm is a check pre-sorted algorithm. And then what that method does is it checks if the input is pre-sorted. If it does, then we're good. And if it's not pre-sorted, then it moves on to the next algorithm. And this lets us come up with a bunch of independent and rearrangeable methods and then put them together with nested algorithms. And it lets people modify those algorithm lists if they'd like. And it creates a way to reuse these optimizations in different places. So we might want to use insertion sort in more than one place, and we can describe that using this algorithm type. It becomes almost a domain-specific language, the algorithm type. If we wanted to not check if something was pre-sorted, we could call it like this, without the check pre-sorted type, and then it'd dispatch straight to insertion sort. This is not an excerpt from Julia source code, from base implementation, because why would you check pre-sorted before insertion sort? Because insertion sort's really fast on sorted data. It's just an example. I should have said that at the beginning. Anyway, what else is going on here? There's this keywords function. This KW stands for keyword. Those are kind of weird. Why that's there? It's to pass around dynamically scoped variables. There's a lot of things you might want to keep track of in sorting. You might want to pass things from one method to another, from one optimization to another. Like low and high are the first and last index that are going to be sorted. If you're working with partial sorts, those can contract as you realize that only a sub-region is of relevant interest. Or you have an optimization or just an algorithm that breaks up the input into two parts, and then you want to sort them recursively. You should set low and high, and those should be passed through all the methods. And some other ones you might want to keep track of are minimum and maximum, which is the extrema of the input. And that's useful for optimizations of all, whether you can do counting sort reasonably. Counting sort relies on a very tight range between minimum and maximum. And once you've computed it once, you don't want to recompute it. And I also don't want to pass that through each method explicitly. And so this keyword mechanism provides that. And I use it instead of, I use named tuple in the argument position instead of keyword args because it allows dispatch and there's zero overhead. It's kind of like globals and kind of like keywords, but it allows dispatch and there's no overhead, no recomputation. And so it's as if I was passing them all through explicitly in positional arguments, which, I mean, that is what's happening. It's just you can't really see it because it's hidden away. And there's this scratch space thing. Some algorithms want scratch space, like scratch quicksort, like radix sort, like merge sort. And we only want to allocate it once. There should not be, when working with scratch space, you don't want to like make a scratch space, let it be garbage collect, and make a new one. If we had great escape analysis, that might be fine. But without that, we need to allocate it once and then pass it around. And the tricky thing in here is we can't allocate scratch space at the top level and pass it down the call chain, because at the top level, we don't know if we're going to need it. We don't know what algorithm we're going to dispatch to until we've done some analysis. We don't know if we're going to need the scratch space, and we really don't want to allocate if we don't need it. So for that, we need to pass it up the call chain, because we might go down one branch, realize we need scratch space, and then finish up, come back up, go down another branch, realize we need scratch space, and we want to share that. So this is even closer to a global variable than what we were working with before, but it's still implemented with zero overhead. We're not actually using global variables. It's just similar to that behavior. And the way we'd implement this is by returning scratch space. How do you get something up the call chain? You return it. So this underscore sort bang returns scratch space, not the sorted vector.
Does it always return scratch space or keyword?
It only returns scratch space. Okay. Maybe it should also return keyword.
I mean, if you don't need it, you don't need it.
Yeah. So for the other keywords are low, high, min, and max. Low and high, it makes more sense to do like a recursive paradigm, because when you set low and high for a sub-algorithm, you don't want your parent to have that restricted low and high as well. Whereas scratch space is kind of different in that way, that it's just passing it around. It doesn't matter what happens to it. There's very little semantic in the scratch space. In retrospect, this keyword design was made before I knew what a dynamically scoped variable was. Like, maybe this should be changed. This is letting folks, this talk is giving you a view of what's going on right now. It's still internals. It's still subject to change. I appreciate like where it should go. Yeah. Anyway, this is a screenshot from a REPL. This is the default stable sorting algorithm. Fun fact, this looked so bad. This is custom printing for the algorithm type. It was a lot worse without that custom printing, because this predated abbreviated type signatures. So it was like, I mean, this is O of n. It was O of n squared length. Yeah, anyway. What's n? N is the number of nests. So if you have something of a type, nested types like check pre-sorted, if you nest that n deep, then the length of that without abbreviated type signatures is O of n squared.
Every other type references all types.
Yeah, really bad for SciML. Anyway, if you have nested types, the default printing from like Julia 1.9, maybe 1.8, definitely in 1.8, very poorly displays, very large. Anyway, we've fixed that. But this is what we're using now? Yes. This is the default algorithm. And let's walk through, I mean, one caveat, like maybe this is bad. Like, does anyone really care about sorting performance? Unclear. If the answer is no, maybe we should just revert all this. Like, this might have been a mistake, but this is currently the case. So the first thing we do is a missing optimization. So if the element type is a union of, say, float 64 and missing, then we'll be like, wait, hold on, okay, 15 minutes, this is great, there's plenty of time. We filter the missings to the end. Like sorting filters missings to the end. That's just in the doc string. Missings go at the end. Some people want to be able to put missings elsewhere, but not enough people have asked for it to put it in base. We'll see where that's going. Anyway, this optimization does that at the beginning. By default, what we would be doing is using the comparison function and see, like, is 4 less than missing? The answer to that is no. Missing is greater than 4. And that comparison. Well.
Oh, font size.
Thank you for the font size. Anyway, this is slow because there's like dynamic dispatch almost. I mean, probably not dynamic dispatch because unions with missing are efficient, but we don't want to be doing that. We'd rather first filter all the missings to the end and then work with non-missings. So, what the? Okay. Why is my camera on? That's creepy. Anyway, Microsoft PowerPoint. So missing optimization filters all the missings to the end and then wraps the remaining vector with non-missing vector, which is an internal type that has an L type that is not missing and just asserts that it's not missing. So then you've got a not missing vector wrapping a vector with L type that's a union with missing. And we just assert that all the missings are at the end. And we enforce that by when we construct the thing, we put all the missings at the end. And then we proceed with whatever's next. Or if that optimization wasn't applied, we just proceed with whatever's next right away. Yeah?
When you do the missing check, you have to scan for the missings and then you do the is sorted check. Is that fused somehow as an optimization? Because you can do the both checks at the same time.
Yeah, that is not fused. And have I actually benchmarked fusing those? No, I haven't. Maybe it is faster. I think that it probably won't be much faster, but
it's reading the memory, I guess.
Yeah, it could be.
Since you have that beautiful slide up there, a question: how do you come up with such heuristics? In particular, given similar to the previous question, that some of these checks for making decisions also have the runtime cost.
Yeah.
So how do you come up with this? I mean, like, is it a lot of trial and error? Like, you know nothing about sorting, pretty much. So
Yeah.
how much is trial and error? How much is known in the discipline?
A lot of trial and error, a lot of benchmarks, and a lot of these are free. The missing optimization is free if the L type doesn't have missing. The bool optimization is free if the L type is not bool. Most of these are free or very cheap, except later down the chain there get to be some expensive ones, but they're warranted because they allow for much faster algorithms. And it's in trial and error. Yeah. As for fusing missing and is sorted, most inputs aren't sorted. If your bottleneck is sorting and your inputs are typically sorted, what am I here for? So.
Do B time on the sort, and then after the first iteration, it's always sorted.
Yeah, yes, that's something to be aware of when benchmarking sorting. If you're benchmarking an in-place sorting operation, you need to set evals to 1, or you need to copy in the data. Because otherwise, yeah, very easy to be like, wow, this sorting algorithm's really fast. When you do at B time sort of X, no, that's bad. Anyway, okay, so Boole optimization is next. This one was to prevent a regression. I did some stuff, and I had a regression for sorting Booleans. Sorting Booleans? What? Why would you do that? I don't know, but I didn't want a regression. So sorting Booleans, you just put the falses at the beginning and the trues at the end. There's a special case algorithm for that. There's some compile time cost, but who cares about time to first X? This is Julia, right? Anyway, it's also in the sysimage, so like it's probably fine. I don't know. Yes. Yes. Counting sort, though, allocates a vector. And yes. Yeah. So anyway, once you've done those, if you've got fewer than 10 elements, you should just use insertion sort. And that's the next step. That's small. Base.sort.small is an algorithm that has a parametric type. So that 10 is actually a compile time known constant. Less than 10, we use insertion sort, which is that next one on the list. And if it's more than 10, then we use the IEEE floating point optimization. This one's actually a pretty old optimization. What it does is if the input is a vector of IEEE floating point numbers, all of the same size, and we're sorting it in ascending or descending order, then we can use a cool property similar to missings, how we didn't want to compare and check if something's missing. Floating point comparisons are a little slow, like nanoseconds slow, but still could be faster. It's faster to compare integers. So what we do, and the reason floating point comparison is slow is because nans. So we want to swipe the nans to the end, and then also partition based on if it's greater than or less than 0. Because the bit pattern of floating point numbers is not quite the same as the bit pattern for integers with respect to comparison. You cannot reinterpret a floating point number as an integer and get the same order of comparison, even without nans.
Just the sign, the negatives are in the wrong order.
Yeah, the negatives are in the wrong order. Bummer. So we split them based on positive and negative, and then reinterpret as integers, both halves, and swipe the nans to the end. And I think all that's in one pass. Yeah?
So going back to the Boole optimization, what's the reason, is there a reason we do this instead of just dispatch, doing like a kind of an explicit shorter dispatch for Booleans, like with a different method?
Yes, there is. If we, what? Oh yeah. Is there a reason we use this giant nasty system instead of just normal dispatch for bools? And the answer is yes, there is a reason. Also, the question was not that meanly phrased. It was a very kindly phrased question. Anyway, so one reason is if you have a union between missing and bool, what this optimization does was first do the missing optimization and swipe out the missings, and then can still do the bool optimization. So rather than method ambiguity of like, is it a union with missing? Yes. Is it a bool? Yes. I guess it wouldn't be a bool at that point. What we have is like an order. And another reason is because this lets you, I don't know. Yeah, that's the main reason. And because this is like a homogeneous system. To avoid ambiguity for dispatch, all dispatch for underscore sort bang is determined based on the algorithm. And so that means there's going to be no ambiguity. It would be possible to do it a different way, but this works and has 0 overhead, so that's why we do it that way. So after IEEE floating point sorting is checking if it can be mapped to unsigned integers. And that's what I was talking about with these IEEE floats, how you can once you have them all the same sign, then you just reinterpret them as an unsigned integer. Or a signed integer, I don't remember. Either, great. We do one of them, I don't know which. It was a while ago. And there are other, you can reinterpret chars as unsigned integers. You can reinterpret signed integers as unsigned integers. You need to do a little bit of bit twiddling to get signed integers to be reinterpreted as unsigned integers. But it's worth it because then you only have to support, for these like checks, for these counting sort and radix sort algorithms, we only support sorting unsigned integers in forward order. So we do a little bit of bit twiddling and then sort using really, really efficient O of n algorithms whenever possible. And there are some cases where we could extend this. It's possible to reinterpret tuples as unsigned integers and sort accordingly. We don't do that, but it's possible in some cases. So then if it isn't reinterpretable as an unsigned integer, we check if it's sorted, and then we perform scratch quicksort if it's not sorted, with insertion sort as a base case. Stick around for later for what scratch quicksort is. Anyway, if it is reinterpretable as an unsigned integer, then we try counting sort if appropriate, and we try radix sort if appropriate. And to do those, we need to compute the extrema. That's the minimum and maximum value, so that we only have to radix over the necessary bits, and we only allocate what's necessary for counting sort. And then we also consider insertion sort or maybe scratch quicksort, all based on the size of the input and the range of inputs. So that's all. That's the current system. Limitations: the internals are complicated and hard to work with because they're complicated. And when folks start depending on the internals, this is going to be such a mess to maintain. Don't depend on the internals, folks.
I guess sorting algorithm wants to hook into them to add new sorting algorithms.
Yeah, and that's why sorting algorithms, old versions of sorting algorithms are broken on new versions of Julia, because they depend on the internals.
Is there anything else that cares about this?
I don't think so. Yeah. Don't do it. I'd like to thank Nicole Eichmeyer and Peter Michael Osera for funding this presentation happening. A lot of people helped review and contribute to discussions and such. Special shout out to Lucas Schwart and Jeremy Knussel. I've never met them in person. I don't know. They're just like random people who helped with documentation. Thank you so much. Anyway, that's all. Do we have time for questions after? Or was that countdown to end?
Yeah, sadly, we do not have time.
Okay.
We had some questions throughout first,
yes.
Fortunately. So yeah, we do not have time now. We've got to move on with Mose. But thank you very much.
Thank you for the questions, by the way. Really appreciated them.
All right, our next speaker is Mose Giordano, who's very well known as a past winner of the Julia Community Prize, in fact. He's currently a research software engineer at UCL. He's done a lot of work on Binary Builder, especially is what he's the hero of Binary Builder, really, and has done many, many things in the Julia ecosystem. So much stuff that he's going to talk about a cool-looking project that I didn't even know about today, running Julia on some exotic hardware.
Okay, can you hear me? Yes, cool. Hello, so I will talk about running Julia on the intelligence processing unit. I will start from the acknowledgements. So I actually didn't start this project. This was initiated by Emily and Luke at the Simula Institute. I just recently picked up this project and expanded it. And my work was funded by my department, the UCL Center for Advanced Research Computing, and I got also some help from my colleagues. And I want to thank all the people in the GPU compiler ecosystem. So Valentin, Tim, Valentin, Gabriel, and anyone else who was in the chat was asking many stupid questions. And I also got some help from GraphCore engineers. GraphCore is the company developing this accelerator. And I also used the Simula X3 system at the beginning of this work. Next. Yes. So who I am, if you don't know me, I am Jose. I'm a research software engineer at UCL. I've been using Julia for about 7 years now, and also trying it out on some interesting hardware. I have another talk about some kind of interesting hardware tomorrow, and Julia for HPC mini symposium. But most importantly, I'm not a compiler engineer. Maybe you will understand why I'm specifying this later on. What's the IPU? So IPU is this accelerator. So you can see here a picture of a board. So on each of these boards, you will find 4 IPUs, these 4 chips. So this board delivers 1.4 petaflops of AI compute, means 16-bit floating point numbers. So it has a memory of 3.6 gigabytes in total. So each IPU has 0.9, about 900 megabytes of memory. And we can go and see a zoom in. So this is one IPU, one chip. And this has 1,472 cores. And each of them has 6 threads for a total of almost 9,000 threads. And again, the memory for the entire chip is 900 megabytes. And you can find some other numbers here. But what sets the IPU apart from the other kind of systems that we know? So CPU is mainly designed for scalar processing. You know that you can have multiple cores nowadays, but still each core is basically designed for scalar processing. Instead, the GPU is designed for single instruction, multiple data. So you can operate on a large quantity of data, but a single instruction at a time. Instead, the IPU is a massively parallel, multiple instructions, multiple data. So each core can actually run a different function, a different program at a time, which is a big difference compared to the GPU. So here are some other numbers to compare the IPU to the NVIDIA 100 GPU. So again, number of threads, it's about almost 9,000 for the IPU. Instead, it's around 7,000 for the A100. The memory for each core is 600 kilobytes. So in the IPU, each core is called a tile, because this looks like a tile covering the IPU. Instead, for the A100, the memory for each streaming, no, it's called SM. I never remember what SM means. But anyway, it's almost 200 kilobytes. So again, this is much better for the IPU. And if you count for each threads, I think this is divided by threads. This is 100 kilobytes for the IPU and 7 kilobytes for the A100. In terms of vector registers, for the IPU, it's 2 floats, so total 64 bytes. No, bits, sorry. And pick teraflops is about the same, actually, just slightly better for the IPU, but very little better. Programming the IPU. So GraphCore, the company, provides this popular SDK, the software development kit, which is written in C++. So if you want to write a IPU program, you need to write basically like low-level programming. It's in C++. But most of the end users are actually machine learning scientists, and that's why it's called intelligence processing unit. And they provide like implementations of PyTorch and TensorFlow that are aware of the IPU. So this is in Python. But there is this distinction between you can do either low-level programming using a low-level programming language, like a C++, or high-level programming, but only with the tools provided by the vendor. And again, at the moment, this is specific to the domain of the machine learning. So there is nothing in between, like using a high-level programming language for doing more generic programming. So who knows what we can do about this? How you program an IPU is basically you need to create a graph or operations that you want to run. That's why the company is called GraphCore. You define this graph, and each vertex is a function, and all the functions can be different. So this is, again, a big difference compared to the GPU. So each of these nodes in the graph are the vertices of the program, and they can be either different kernels completely or the same kernel but fed with different data. So maybe you can combine the data, the input data to your program in a different way. And you can have multiple steps, so you can have like a first run of operations in all the styles, and then you get a new array tensor in output, which is used as input to some other operations later on. So this is more powerful, but from powers, how is it? You get more responsibility. Programming the APU is much more complicated, right? But what's next? What's a compiler? So this is a kind of the diagram of how a compiler works. This is specific to Julia, but actually the kind of pipeline is in common to most of compilers, I think. So you have some source code written usually in a text file. You have the lexing stage, then the parsing, where you get the abstract syntax tree. And then there is the lowering, after which you get some other intermediate representation, basically, of your code. And at the end of which there is the LLVM IR. But this is part, so the first, this green region is part of the front end, so what the Julia front end does. But after that, you can have multiple other stages that are done by the back end, which in this case is the LLVM. But the important thing is that you can get to the same LLVM IR from different front ends. For like you write some C++ code or Rust or whatever, you can maybe get to the same IR. So whatever the front end has done before doesn't matter anymore. And after that, it's only LLVM doing some optimization passes and generating finally the code for the native code for the device. And this is important because we want to basically generate some IR for our device and then compile the native code. So the only existing implementation of Julia is based on the LLVM compiler, and in Julia, probably most people already know, but you can see these steps of the compilation pipeline. So for example, with the dump macro, you can see the AST, and with the code typed macro, you can see the typed lowering of the code, and then the LLVM macro, you can see the LLVM intermediate representation. You can actually also stop before optimization with some other keywords here. And then finally, there's the code native macro to see the native code generated by the expression, this one. And for more details, there is a great talk by Valentin about this. But this is important because actually both Julia and the compiler used developed by GraphCore for generating code for the APU are based on LLVM. So LLVM is basically a common language for both Julia and use in the APU. Yes. So basically, we developed this package called the APU Toolkit. It's registered in the general registry, so you can install it if you have an APU. And we use basically Julia to generate the LLVM IR. So the overall goals of this package are interfacing the polar SDK, because that's anyway essential for writing the program overall. But also we wanted to explore Julia's metaprogramming capabilities to simplify how you write an APU program and reduce the boilerplate code, which is a lot. And also use Julia code generation capabilities for generating native code for the device. So this is what our pipeline of the package looks like. So you write some Julia code, and we have the bindings for the Polar SDK, and also use the GPU compiler framework, which at this point is clearly a misnomer, but it's okay. To generate some LLVM IR, and this is literally written to a file. And then used the POP-C compiler, is the popular compiler for generating the APU code, native code for the device, which then can run on the accelerator. Yeah, again, we are using GPU compiler for this, and we have all the usual GPU compiler limitations. So the code has to be statically inferred and compiled, so no dynamic dispatch at runtime. We cannot use functionalities which require the Julia runtime, for example, the garbage collector, so no memory allocations. So we cannot use the scratch for sorting, because I had that problem, the scratch space, but we can change the default sorting algorithm when we do this. And also we cannot use external binary libraries because we don't have access to like x86 libraries on the IPU because it's completely different architecture. So I already mentioned that the LLVM IR that we generate is independent from the target, from the front end in the end, but also it's mostly independent from the target that you're generating the code for. And we're actually using this because we're generating, in this package, we're generating code for the x86 target, yes, for the host, basically, which is a hack, but it works. It works as long as you don't use the SIMD instructions, because it will generate SIMD instructions of registers with like 512 or 256, depending on your CPU, which is completely wrong for the IPU, because it was just 64 bits. But apart from that, it usually works pretty well. And so GraphCore also recently open sourced their fork of LLVM, which includes also the backend, which is called Colossus. And I was recently able to link Julia to the fork of LLVM. So I was able to actually generate LLVM IR for the Colossus. It works in very basic examples. I got some other errors in other programs, so it's not very stable, but yeah, we did it. And also it was the first use of the open source fork of LLVM by GraphCore. So first code example, there will be very long code because again, it's very verbose how you write a IPU program. So here we are just generating a computing pi. This is like an exercise by Owen Kwen, the head of research computing at UCL. He likes trying this algorithm for computing pi on different programming languages. So we are computing pi. Also, this algorithm is very bad for single precision, and on the IPU we have to use a single precision. So if we don't get 3.14 or whatever, don't worry, it's okay. So basically here we are using this macro at Kotlin to generate the, to define the kernel of the functions that we want to run. And we are, I think, yeah, we are parallelizing on all the 1,472 cores. And we get blah, 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 blah. We get, as a result, 3.1499, okay, fine. And this took, running on the device, took 123 milliseconds, which is pretty good. On a CPU will take, I think, a couple of seconds, something like that. I did the same program also for written in C++. This is only the codelet. Codelet is how they call the kernels. And I hit the rest of the program. And this took 0.14 seconds, which is actually slightly slower. But there is no magic going on. It's just Julia generating, in this specific case, slightly better IR. And, but I believe this is mainly due to Julia doing a better loop unrolling. But anyway, I think this was a good showcase that Julia can be a valid front end for writing kernels, codelets for the IPU. Okay, stochastic rounding is also similar to the topic that was introduced before. So R is a continuous set of numbers. But computers have to use a subset, a finite subset of R, which we call, in this case, F. So when computers do operations with limited precision, they have to give a result in F. So your number, the true result of your operations X has to be approximated by this X hat in F. And on CPUs, this is usually chosen deterministically by rounding always to the nearest number in F. So this is called nearest rounding. But stochastic rounding is an alternative approach for rounding your operations. And instead of always running to the same number, sometimes you round to either the previous or the following number in f with some probability. One probability could be half and half, but it's more interesting to round with a probability which is proportional to the distance to the two adjacent numbers in f. So in this case, like your actual result in R will be x, and sometimes you round to x2, sometimes you round to x1, but more often to x2 because it's closer to x2. Our result is closer to x2. I was actually introduced to stochastic rounding by Milan again. So stochastic rounding is interesting because on average, especially if you use this probability, which is proportional to the distance to the numbers, because statistically it retains some information which is otherwise lost when using deterministic rounding. And so you can smooth out the numerical rounding errors due to limited finite precision. This is especially important when using very low precision floating point numbers like 16 bits. And instead, when you use deterministic rounding, you introduce a bias, basically, in your operations. And DIPU, this is important. I'm talking about this because DIPU is one of the very few processors in the world available which have hardware support for stochastic rounding. So let's do some exercises. So we generate a function which does the naive summation of numbers instead of using the sum function in Julia, which will do pairwise summation, completely defeating my exercise. And we create an array of 3,000 times the number 0.9 in half precision, so with 16 bits. And if we do the naive summation, we get as a result 2048, which is very far off from the actual result. And you can make this as bad as you want because actually 2048 has a machine precision of 2. So if you try to add 0.9, you always actually adding 0 because the machine precision is much larger. And instead here I'm running a program on the IPU with stochastic rounding enabled, so this argument true to this function, which is running the same function again, so naive sum, but 100,000 times. So maybe you can understand that we are going to get a distribution of results instead of a single result, deterministic result. So we run this program and we get this nice plot. So the orange line is the result with the nearest rounding. And instead, this is the distribution of the result of the sum computed with stochastic rounding. And we can compute some statistics on this distribution. You can see the extrema are within, I don't remember now, I think it's 130 from the center, yeah. Because the center, the mean of the distribution is almost exactly the expected result of 3,000 times 0.9. Standard deviation is about 29. The median is exactly 2,700. Okay, so this is still not always approximately equal to the expected result, but still it's pretty close.
The times are shown, the run times are being shown.
Sorry?
When you put the mouse, I see some time numbers. Are they the run times? When you mouse over those cells, I saw 684 microseconds. Was that the runtime of that cell?
Yes, this is Pluto, not about. Yeah, sorry. Yeah, yes. No, okay, so I have something later about this. So we can also solve differential equations on the IPU using a package called the GPU, which again, it's a misnomer at this point. So what we are doing is to solve the Lotka-Volterra system, so the prey and predator system, using half precision with stochastic rounding enabled and disabled, so we can compare the results of the two, and also on the CPU to see which will take as a ground truth. And I'm generating here, basically it's complicated, but I'm generating a grid of parameters, so I can pass 1,472 different sets of parameters, and I can run these many differential equations in parallel. So we can define the function for the system. the function for running this on the CPU, and then the very verbose program on the IPU for doing the same. And then doing here the for loop for running the program with stochastic rounding enabled and disabled. We do this, and we get, for the runtime, we get with nearest rounding, the runtime is 14 milliseconds, and exactly the same with stochastic rounding. So again, this is very important because the IPU has a hardware support for stochastic rounding. It has no performance, no runtime penalty. And we see the results. So these are the results. So the blue line is double precision, which again we take as the truth. The orange is nearest rounding in half precision, and the green is stochastic rounding with half precision. And you can see that stochastic rounding basically makes half precision useful. Like you recover precision that you lost. I started from this plot because it has a very bad result for nearest rounding. If I can change the parameters here to look at another plot, you can see in a few seconds that, yeah, it's not as bad, but still you can see the difference between nearest rounding and stochastic rounding for half precision. And we can also look at the other variable in our equation. Yeah, so again, you can see that stochastic rounding is always recovering precision lost with a low precision floating point numbers. Last bit is automatic differentiation. I will go very quickly, but I assume that here everybody knows about enzyme, like the auto differentiation engine, which works at the LLVM level. And this is great because in this way we can use this to compute the derivatives of our programs at compile time before sending to the device. So on the device, we will just run the exact derivatives of our programs. And yeah, some examples of using enzyme. And what we want to do is to minimize the Rosenbrock function using a derivative computed by enzyme. But again, the enzyme will run basically on the host, which is great. So this is the function definition of the Rosenbrock function. This is what it looks like. For those who don't know, it is basically this function, which has this very narrow valley. So when you try to minimize this function, it's very easy to get into this valley, but it's very hard to find the actual global minimum, which is this 0.11, because yeah, you get stuck somewhere in here. This is also what it looks like from the top. So again, the minimum is this spot. So this is the gradient of the Rosenbrock function, and we can ask enzyme to compute this. I think this is the second argument, which is easier to read. There is basically here the x squared. Ooh, what was it? So this is x squared. So computing, multiplying the first argument. Then we subtract this to y, which is the second argument, and multiply the result by 200. So yeah, the enzyme was able to compute the derivative correctly, which is a good test. And so yeah, I'm now running another program, minimizing the Rosenbrock function using Edelman algorithm. And this was nice to implement because it looks exactly like the paper. If you like compare side by side with the paper, the code is exactly the same. And I'm returning the number of steps after which we stopped, so when one of the conditions, the stopping conditions, were met. So again, we create a range, a grid of parameters, parameters of the initial points, and then we see how many iterations we took to stop the minimization process. So we run this program on the IPU. So we have 33,000 points, and it took about 30 seconds to run, and this looks like this. So we can try to zoom in around 1.1, and as a sanity check, it took just one step. So Z is the number of iterations, actually the square root of the number of iterations. And if you start from the global minimum, it didn't move, so it's OK. But you can see that in general, when you are in the valley, it took very few iterations to stop, to find some conditions to stop. But if you get far away from the valley, it takes longer and longer before reaching some solutions. And if you want, here there is the LLVM-IR of the program, which is actually basically this. yeah, it's basically this, because the rest is metadata. But again, this is great because you are generating very short code to run on the device. So conclusions. How did it go? So every time that I was asking for help in the GraphCore Slack, because I was having some problems, the average answer that I got was, "You are the first one trying to do this." Great. Yes, I could tell that, yes. What we achieved. So we developed the first third-party programming model for the IPU. So in a language which is not supported by GraphCore. And this was made possible by the LLVM compiler framework, which, again, I think it's a great success story for Julia for using LLVM. So Julia allowed us to do general purpose programming on the IPU using a high-level programming language, which, again, is something new for this device, outside of the machine learning niche. So we propose non-trivial programs, I think, using third-party packages, which is also something that you cannot do on the IPU using the C++ programming model for the kernels, because, yeah, you cannot link external binary libraries. And also, thanks to Julia's introspection and metaprogramming capabilities, we slightly simplified how you write IPU programs. We could also use a single and half precision floating point numbers, including stochastic rounding. We also did the first use of the GraphCore LLVM fork. Overall, I was not concerned about performance, but I showed that, at least in the simple Pi example, performance was actually slightly better, or anyway, comparable with competitive with C++1. There are some limitations, of course, but some of them are in common with the GPU ecosystem. So you cannot run any arbitrary Julia code on GPU. We could only wrap a subset of the Poplar and Poplibs libraries. We are currently using a light C++ shim for defining the vertices, defining the codelets. Ideally, we would like to define everything in LLVM-IR. We targeted Colossus, but this is very experimental, so more work will be needed to improve this. We didn't figure out how to integrate GPU arrays. I think this is a hard problem because how you program a IPU is very different from how you program an IPU. But if someone has some ideas, please come talk to me. Currently, I have no access to the high-level threads, so I'm actually, the maximum parallelism that I could achieve was 472 cores, so I didn't have access to the individual threads. But I discovered last week that it should be possible to do that. So I will look into that in the future. And if you wanted to try Julia on the IPU, you can, because there is a cloud service provider called Paperspace, which offers free time on IPU. So if you go to this repository, Julia IPU demo, you find the instructions to run this. And with that, I'm finished.
All right, we have 1 minute for questions.
I'm curious how stochastic rounding is supported at the hardware level. A little bit off topic, but
so basically,
how is stochastic rounding supported? Is the question.
So they have a PNRG on hardware, and this is connected to the floating point unit. So it's just all the same on the same chip, and yeah.
Accessibility shortcut.
Okay, with that, let's thank Dave one more time. And I have been asked to remind everyone about the poster session, which will be at 6 p.m. on the 4th floor of this building, which you can get to from either elevators, I believe. And you will not want to miss it because the posters will be very interesting. And there will also be free food. But, you know, mostly the posters, right? I mean, and now we're going to do lightning talks, so this is the hard part of my job. I believe Lilith is back. Yes. All right, Lilith is going to talk about Quick Draw, package deployment system. Everyone loves deployment, so sounds really interesting.
Hello? Hello? I think it works. Okay. So this is honestly a kind of silly talk. This is honestly a kind of silly package deployment system, but it's very simple. So the goal here, this is motivated by a real world experience I had. I built a Julia package that provides an end user experience, and I had a user who didn't know Julia, didn't want to learn Julia, isn't a programmer, but I made a GUI, and I want to get this GUI onto their computer. So that's the story I have, and the solution that this provides is the developer defines a main function, so it's like mypackage.main is the function you call, and upload the package to any PKG compatible hosting service. Like, that sounds complicated, but that's just like open source on GitHub is a great option. If you want to do closed source stuff, I don't know, figure it out yourself. And tell your user to paste this single command into a terminal. Not all users are going to be able to paste a command into a terminal. That is something that requires some technical expertise, but it's certainly easier than installing Julia, and I mean, I guess you can install Julia with that method. But it's a fairly straightforward system. So what does this look like? It looks like a live demo. Okay, so let's say I have this. This isn't the one I actually had, but it'll work, maybe. So I've got this Minesweeper game. Great. How do I install it? Run this command. Okay. I'll just do that. Oh, caveat, time to first plot. I didn't really worry about it, which is so bad. It should really, oh, great. Wow, that was way faster than expected. Anyway, so it says installation succeeded. Double click on Minesweeper to run the program. It's currently located there. What does this mean? I don't know, but there it is, right here. So double click on this, and it opens a little thingy. This is downloading the general registry because it automatically updates the package every time it runs. That is something I did on purpose, but it's also possible to do it differently. And then I can play Minesweeper. Yeah, there we go. Anyway, so that's, yeah, woo! Live demo works. In theory, you should be able to go to this URL, and follow those instructions on your computer, even if you don't have Julia installed, but all of you have Julia installed, so not a real demo. It'd be hard to find a computer without Julia installed in this menu. Anyway, and it should just work. File an issue if it doesn't. So what's behind the scenes? This is the command that I say to run. It is very similar to the Julia up install command. Basically, download this install script and then execute it. Security implications, if you don't trust me, don't do this, because I don't know what's on it. I mean, I do, but, or you can cat this URL and read it if you want, if you don't trust me and want to catch me in the act and don't want to run malicious software, which it's not, but like you have no way of verifying that. You can download it instead of downloading and running. But anyway, if you trust me and you trust the package developer, then you can run this command and it will download the script and run it. And this final thing in square brackets should be different for different packages you want to deploy, because somehow you have to tell the script what package to run. So this is what's going on in the script. First, it runs julia-v to check if Julia's installed. If it is installed, vroom vroom, use that version. If it's not, it uses Julia up to install it. Then it creates the project, a shared project for this package, named based on the name that you gave the package, that you gave the command, and then creates a little shell script, and that shell script is going to try to update the package and then launch it. And then it saves the shell script to your current directory or the desktop or whatever, and tells you where that shell script is. And it gets automatic updates. Yay! You can turn off automatic updates. I mean, no, there isn't a feature for that right now. In theory, it could be supported if people wanted to turn that off. If you try to update it and the internet doesn't go through or whatever reason the update fails, it will tell you update failed and run it anyway. I've deployed this at a tiny scale and it works okay. I don't recommend this for like really polished stuff. Definitely like use package compiler and stuff. But if you want a very quick, simple solution, maybe. Limitations, Windows. There is an option for Windows. Okay, sorry. There is an option for Windows. It's just a different command you paste, and that command operates with a different mechanism, also works reasonably well. I have tested it. Hopefully it works. But it's a different approach. And the fact that it's a different command for Windows and non-Windows is a little unfortunate, but whatever. Security. So when you install Julia using JuliaUp, it's the exact same model. And you have to trust the host of the script that you're getting. And for JuliaUp, that's install.julialang.org. Seems like a reputable URL. It ends in .org. I don't know. For this, I'm hosting that on lilithhafner.com, so maybe it's reputable, maybe it's not. Anytime you're downloading software from an unknown source and running it automatically without inspection, like that's a security vulnerability. Yeah, consider that. It requires the user to be able to interact with a terminal. Ideally, if you're making a GUI application, someone can get it with just a GUI, like don't need any sort of terminal anything, download the thing, double click it, that sort of thing. This is not quite that simple, alas. Final limitation, time to first plot. This does do pre-compilation, but it's still like not ideal because the pre-compilation happens on the user's machine, which when I download new software, I want it to just run. I don't want it to be like, I'm compiling myself on your computer. So yeah, those are some limitations. Again, I'd like to thank Peter Michael Sarah, Nicole Eichenmeyer for funding. Yeah. Questions?
Yes?
How would you feel about being able to make it not install into home directories, like into a temp directory?
Question is installing somewhere other than home directory.
So the install location is, one, it's creating a shared Julia environment as opposed to a temporary environment so that pre-compilation works. It could be a temporary environment, and then you just have to re-precompile every time you double-click the thing. Oh, I hate re-precompilation. But this is mobile, so I can like make a folder and just like move it. If you don't like it there, put it here. Should still work, I hope. Still downloads the general registry every time you double-click it. That's kind of bad. Wish that didn't happen. Anyway, so it's relocatable in that sense. Yeah?
So if a user, let's say, use Julia, download this, and install Julia, is there a way for them to uninstall both this and anything that has been installed alongside it?
Question is about uninstalling.
The answer is no. You need to, if you delete .julia and you delete wherever JuliaUp puts stuff.
Not Julia.
Also Julia.
Oh yeah, the binary is not in .julia, but Julia itself is in .julia.
Yeah, so the answer is no. There's no good way. Yeah, that's a limitation. If I was under the impression this was a useful tool people wanted to use, then that's something that could be done.
Can the same repo or package work with package compiler and with this installation method?
Yeah, so this installation...
Can it work with package compiler?
Oh yeah,
is
thank
the question.
You. So package compiler works, and this works, and you can have a repo that has this and package compiler. in parallel. They won't like work together, but they don't get in each other's way. What this requires is that you can call package.main. That's the only requirement. So yes, does work. I hope.
Okay, that's it. Thank you.
Thank you.
Okay, having solved deployment, we are now going to solve garbage collection. We've got Nathan Daly from Relational AI and Diogo Neto from Australian National University. And also Relational AI. Okay. To talk about really exciting, late-breaking developments in Julia GC and possible future of the Julia GC.
Do I allow it to connect? Yeah. Okay. Yeah, it worked. I tried it. It worked. How do I stop mirroring? How do I stop mirroring? Oh, here. Okay. How did everybody else do this? Okay. And okay. Cool. Am I ready to go whenever? Do I just start? Yeah. Okay. Cool. Hey, thanks everybody for coming to our talk about updates to Julia's garbage collection. And, oh, there's a microphone. Where? Here. Aha. Thank you everyone for coming to our talk about developments in Julia's garbage collection over the last year or so. It's going to be a pretty quick lightning talk, so I'll keep it brief. We're going to, there's a lot to cover, but we'll just give very high-level things. So the problem we've been facing at Relational AI, which is performance of Julia's garbage collector, and the solution we have invested in, which is basically 2 tracks. One is improvements to the current mark and sweep GC that Julia has shipped with, and investing in new GC algorithms for Julia through the help of the MMTK framework. We'll thank the teams who have been involved in this work. And finally, Diogo will cover the detailed performance results, which is why you're all here. So the problem that we were facing at Relational AI for a while is basically struggling with the garbage collection performance in production, which has been affecting our users and preventing us scaling up. So in some of our workloads, we would see GC percentage time just higher than we would like, which harms our throughput. If we see long GC pauses, that harms our user-facing latency. And we were finding that we weren't able to scale up. So adding more cores to our deployment machines doesn't necessarily result in faster production because the previously single-threaded garbage collector was acting as a serial bottleneck. And here are some example numbers that kind of validate that. So in this benchmark from the open source benchmark suite, we see up to 40-second maximum pauses for manually triggered full heap GCs, and that's long. And then we were seeing in some user scenarios 30% or sometimes 50% GC time. So as a solution, we have, like I said, made these 2 sort of tracks, these 2 tracks of investments in Julia's garbage collector. The first track is that together with MIT Julia Lab and Julia Hub, we have been, mainly led by Diogo, we've been working on improving the existing mark and sweep garbage collector in Julia. And we're really excited about the results there. You'll see them at the end of the talk, but the performance has dramatically improved in the latest versions of Julia. And so we actually feel that we're reaching the state-of-the-art mark and sweep GC. And the next medium-term approach will have to be to investigate different GC algorithms besides mark and sweep. And so to that end, in parallel, we have also been working on a separate track for the last year and a half or so with Australian National University, who run the MMTK framework, to investigate alternate GC algorithms besides mark and sweep. So we have first been focusing on the IMIX GC algorithm, which is a moving or copying bump allocating garbage collector. And that has been going really well. We're going to have some initial results at the end on IMIX in Julia. But in the numbers that you see today, they will actually be for non-moving IMICs, because while we think that moving is not too far away, it wasn't quite ready for a fair comparison here. So, and then in the long term, IMIX is still a stop the world collector, and we're hoping to get ultimately to a concurrent GC like LXR, which is a world-class, one of the fastest concurrent GC algorithms out there, and that also comes from the ANU Steve Blackburn MMTK team. And the last thing that I want to cover on this track is we're really happy that one of the outcomes from this that we've been working on is refactoring the Julia code base to allow us to explore new GC algorithms. So in the end, even if we don't end up with MMTK as the source of our backend, GC backend, we think that this work will allow us to explore other GCs as well. So thanks to all the people who've been involved, Steve Blackburn and Eduardo and Yi from ANU, Diogo and Valentin from MIT Julia Lab, and now Diogo works for Relational AI. So Diogo, Karen, and myself from Relational AI, and Gabriel, Oscar, and Jameson have been helping a lot from Julia Hub. So thank you. All right.
Okay, thanks, Nathan. So I'll be talking about the performance improvements that we landed for the 1.10 stock GC, and also talk about some of the performance numbers that we have for the MMTK integration for Julia. So in 1.10, we gave the first steps towards enabling the use of multiple threads in the Julia GC. And more specifically, our work has been about parallelizing the mark phase of the garbage collector, and has also consisted of few refactors that allow the part of the sweeping phase to run concurrently with the mutator threads. So in 1.10, the GC started to look more or less like in this diagram, in the sense that the rough traversal code from the mark phase runs with multiple threads, and a part of the sweeping phase runs concurrently with the mutator threads. So we move a large chunk of the sweeping phase out of the GC critical section. For performance numbers, we'll be reporting here a subset of this GC benchmarks repository that is maintained by JuliaCI, and we'll be focusing on 4 benchmarks, RB3, which is representative of some workloads that we have at RAI that stress GC performance, and also these 3 mutable, and object array benchmarks, which are all the multi-threaded benchmarks that we have in the repo. And just a reminder here that by default, the multi-threaded GC is only enabled if you have multiple mutator threads. So these are the benchmarks in which, by default, the GC would be multi-threaded, and also the benchmarks which put more stress in the GC. So these are the results that we're very excited to share about the work that has been happening in the stock GC. And the general trend that we see here is that with parallel marking, we get a pretty significant reduction in GC time that is coming from primarily from reduced mark time, of course, so that when we have multiple threads running the mark loop, we get speedups which range from 4 to 5x speedup in all these benchmarks. And then the issue is that the sweeping time becomes larger, or at least comparable to mark time. So that when we enable this additional sweeping thread, we are able to move part of the sweeping cost out of the critical section, and we get further improvements in GC time. So that's for the work in the stock GC, and let's talk about the work that has been happening on the MMTK side. For MMTK, the results are very preliminary because moving or object compaction, as Nathan mentioned, has not been enabled in the Julia binding yet, and also because Julia doesn't have a way to put limits on its heap size, which imposes some issues for benchmarking purposes, because we can't really analyze the trade-off between memory consumption and collection time that is being done in the GC. But even with some features left to be implemented, the MMTK results are mostly positive across these GC benchmarks repo. So in this slide, we're again focusing on the benchmarks that I selected before. And on the y-axis of all these plots, we have end-to-end benchmark time. And on the x-axis, we have a heap size measure at a multiple of the minimum heap size required to run the benchmark. So just watch out that these are not scaling plots, but here we're analyzing the trade-off between collection time and the memory consumption that is being done for MMTK. And for some of those benchmarks, we see pretty significant speed up for MMTK, and which is mostly coming from allocation performance, because MMTK uses a bump allocator as opposed to the slower for list one that is used in stock Julia. For the object array benchmark, we currently see a regression that could be coming from a variety of factors, such as different cache behavior as objects get further apart in memory, and when we increase the heap size. We're currently investigating that and should be addressing this performance issue that we have in the this object array benchmark. And yeah, that concludes our presentation. Thank you.
There is 1 minute if there's a question or two.
Why can't sweeping be concurrent for multi-threaded?
Oh, why can't sweeping be concurrent and multi-threaded? I think the answer is that it is, but
yeah, part of the sweeping is concurrent, but so this part which lies inside the critical section is currently not multi-threaded because we didn't see that much performance benefits from parallelizing that specific part. So we saw most of the benefits would come from moving that part out of the critical section, which is what we've done.
Good question. We're using MMTK allow for prototyping with soft real-time type of GCs.
I believe that Imix would not be suitable for that because it's still a stop-the-world collector, but LXR promises like much more reduced pauses, which could be suitable for some real-time applications.
all right, we got to stop there. Next is Shuhei. Yeah. So Shuhei Kadawaki, my colleague at Julia Hub, is going to talk about JET. Tooling around surfacing static type information, static type errors is something there's a lot of interest in the Julia world. A lot of people want more of it at this stage, and so he's going to talk about JET, which is one of the premier tools out there for solving that problem.
Okay, hello everyone. In this short time, I will make a lightning talk about JET. I have plenty to show off, so let's get started. So first, let me give a simple rundown of JET. It's a static code analyzer for Julia, and with JET you can identify bugs and type instabilities, dynamic dispatches that all were seen in Japan. In Julia. Okay. And one key advantage of using JET is it leverages the Julia compiler's type inference engine. So this means by fixing the errors reported by JET, you are actually helping the compiler produce better code. So JET not only helps eliminate bugs, but can also enhance your program performance and reduce the risk of invalidations. Now let's dive into the main topic. It has been 2 years since I initially introduced JET at JuliaCon 2021, and now I would like to briefly run through the various updates that have happened over the period. So first off, I would like to discuss a significant improvement in startup time. And as many of you know, from Julia 1.9 onwards, Julia gains the ability to cache native code. So consequently, JET's fast time to analyze got dramatically improved, and now it is 80 times faster than before. So it's a significant improvement. Yeah. And the performance of JET itself has been improved too. And back in 2021, when I tried to analyze a large package like data frames, it would either crash due to bugs or from outside the code wouldn't finish within a full day or 2 days. I don't remember. So yeah, it never finishes basically. And but now the analysis of data frames takes around 70 seconds on my machine. It's a very good speed, I think. So I say if you attempted to using JET 2 years ago and found it very buggy or too slow or some, and decided it wasn't for you, trust me, give it another go. And yeah, if it's still slow, please file an issue. And moving forward, there have been numerous updates apart from just performance. Firstly, the integration with test.jl was implemented, making it handy to use JET during testing. And fair number of packages already use this feature and incorporate JET into their test suites. And notable early adapters include JET itself and the Climbr core package. And I think the number is increasing. The repo package, which is a convenient entry point for analyzing packages, has been greatly improved too. And previously, in order to use it, we first needed to initialize, activate the target package environment, instantiate it, and take care of pre-compiling and something, and then finally JET could analyze it. But now it's no longer necessary. So if you are able to using target package, report package is now able to analyze it without any rounding issues. And now we have a handy configuration for report package. And for example, when you analyze large packages like data frames, it's quite common to find too many issues cropping up within the dependencies. And in such situations, the newly added configuration named target defined modules comes in handy. And using this configuration, only the errors detected within the module context of the target package are reported. So it allows us to focus solely on the issues arising within the code that we are developing. And there are some improvements in output UI as well. Previously, JET created a custom stack trace-like view that shows incomplete source information, but does not show type information by default. And this made it quite inconvenient when trying to perform further investigation with Qt or code-typed tools. But in latest versions of JET, the analysis results are displayed along with a stack trace-like view, which is similar to what Julia base represents when in a case when an exception is thrown. And this new view is not only more familiar and easier to understand for Julia programmers, but it also makes additional investigations simpler because it's now it's very easy to find analyze and method signatures. And the inference engine used by JET has got smarter. Notable change is the addition of type analysis for immutable pointers. So with Julia 1.9 inference engine, in this kind of cases, the restricted type information about x.value does not propagate into the then block. And as a result, JET wrongly reported a method error there. And this requires us to use a workaround like extracting the field value into a local variable and use it thereafter. But from inference engine of version 1.10 and onwards, the issue has been resolved, and as a result, JET no longer reports false positive errors in such cases. So yeah, I have given a quick updates. So now I'd like to briefly discuss the future plans and conclude the talk. First off, we plan to continue enhancing the Julia compiler type inference. The current Julia compiler's inference engine struggles with handling information about immutable pointers. So when we use type unstable memory, mutable memory, like in this example, we still need the workaround I explained earlier. And the plan is to incorporate escape analysis into the type inference engine and allowing it to treat mutable memory more like immutable memory in many cases and enhancing type information. And if this idea pans out well, it would also address a notorious type instability issue caused by closures to a certain extent. So I believe it's very worthwhile to tackle. next, I'm thinking of porting Jet to Julia Base and making it available as a standard library. And I think by doing so, we can improve accessibility and the maintainability of it, and hopefully gain more users and contributors. Another plan is to implement source level annotations in order to provide a more user-friendly configuration interface. And because implementing a perfect inference engine turns out to be incomplete, turns out to be impossible. So in cases where something is essentially safe but just wrongly reports a problem, it would be very handy if we can silence Jet by this kind of annotation. Lastly, I'm thinking about how to better utilize runtime information to provide a precise and easy to use entry point for package analysis. The idea is to execute a test suite of a package and collect method signatures using method analysis.jl and then reanalyze them statically using Jet. And it can be a package analysis entry point that is very handy to use, like repo package, but more accurate one. And because it takes advantage of the concrete method signatures that only appears at runtime. There are some ideas for UI improvements too. One thing I would like to implement is Kutru like interactive report explorer. So the idea is like a click where error is reported, and it drops you into a Kutru view to investigate code. Okay, that's all I have today. Hearing diverse feedbacks motivate me to make Jet better, so please let me know if you have any compliments or praise or anything whatsoever. So please feel free to share with it.
All right, thank you very much. We're to try to keep on schedule here. I'd like to keep going. So next we've got Simon Byrne, who's been a longtime contributor to Julia numerics and performance issues. He works on the climate modeling project, and he's going to talk about parallel profiling.
All right, thank you. Okay, thank you. So, profiling parallel Julia code. So, with Nsight Systems and nvtx.jl. Nsight Systems is an instrumenting profiler. What does that mean? Well, a sampling profiler is what we have in profile.atprofile, which basically takes snapshots of your code at certain points of time, which is very convenient. You don't have to do anything. You just call it and it works. And it sort of answers the question, where am I spending all my time? An instrumenting profiler requires you to instrument your code, which basically means you stick annotations in your actual code. But it can answer the more complicated question is, what things are happening, when are they happening, what order, how long do they take? In particular, this is very helpful for parallel code, because things often don't happen in the order you intend them to. Nsight Systems is an instrumenting profiler from NVIDIA. It runs on Linux and Windows and also has a viewer for Mac. It has very good parallelism support. As you would expect, it supports CUDA. But it also supports just multi-threading and multiprocessing and MPI. So you don't actually need a GPU to use it. And you can download it for free from their website, although you need to sign up for an account. NVTX is their instrumentation package. So it's a C header-only library, which usually would annotate C code. But you can also build it as a shared library. And so nvtx.jl is a package of Julia bindings for NVTX that was originally used to live in CUDA.jl, thanks to Tim. And then I sort of adapted it, expanded it a bit, and I wanted to use it without CUDA, so I moved it to its own package, and now it lives in a separate package. And the main idea is that it provides a very high-level macro that you can annotate your code with, which the profiler can then access. And we bundle a JLL with it as well, so you don't actually have to download it. It's all included. And it also includes a small hook to instrument the Julia garbage collector, which is very handy for a lot of cases. And the other thing is you can include it as a package dependent. So we make it, it's safe to include as a package dependency, even on systems where the profiler is not available. So you can, it's just most operations become no ops then. Okay, so basics. So there's sort of three main macros. At mark just instruments a single snapshot event. At range is you put it around a block of code, so start around an expression. And there's at annotate, which is similar to at range, except you put it outside a function definition, and then it puts the at range inside the function call, essentially. So, and so here's a very simple example. We define a custom module, load the MVTX package, we annotate a simple function which annotates sleep, and then we put the range around its loop, which calls the function. So we can attach some metadata to it, which is very handy. So things like domain, which we automatically just attach the module. We define a default domain for every module, which is usually how we group code, so that sort of fits with that analogy. You can generate a message, which we just use because it's macros, we can define things like, we can actually just put the line number and file and line number there by default. You can give colors, we just generate a unique one for every annotation. And you can put some small payload, attach like a payload information there if you want to sort of attack other things. It tends to be fairly low overhead. I didn't do any rigorous benchmarking, but it's about 20 nanoseconds if you're not using a profiler at all, and it seems to be about 60 nanoseconds or so when you're profiling. So there's some overhead, but it's pretty low. And so how you use it? Well, you call nsys profile --trace MVTX, and then run your code, and that will annotate it. And so it'll generate a report. You can open the report in the viewer, and it looks something like this. And so you can see there's two threads I'm using there, and they have we can see that there's the outer loop is annotated on the main thread, and the individual function calls are annotated on the inner loop. And one particular nice thing about Nsight is it actually supports you have non-overlapping tasks, and so if the Julia task, the switches task, it's okay if they don't overlap. In fact, they can even switch threads, so you can sometimes end up with tasks that switch threads, and Nsight supports that as well. So parallelism, so that's threaded parallelism. So distributed.jl, it works as well. So just run your distributed.jl code, and as long as they're all on the same process, on the same node, so it doesn't support distributed processes, it'll happily identify child processes, and so you can profile distributed.jl code. The motivation for me was personally for profiling MPI code. And so to do that, there's two ways. The simple one is you do similar to that. You have the profiler, which runs the MPI launcher, which runs the program. So it might be nsys profile, something like this. And that'll still give you, like before, will give you a single file with all the processes annotated. There's actually a more complicated way, which is, but that only, again, sorry, the first one only works if you're on a single, everything's on a single node. If you want to do actually fully distributed run, then you can put the profiler inside the launcher, and then what you'll get is now one profile per process. But it has a very handy, the viewer has a very nice multi-report view where it'll like stick them all and you can open up and view them all individually. And so here's a nice picture from our own code, and you can see sort of, lets you zoom in and out, and you can see we can attach all these different processes are all visible within the one thing. And it also annotates the MPI ranks by default, so you can see which process is going on where. I mentioned you can profile the Julia garbage collector. So we build a small library which hooks into there's one hook into the Julia garbage collector, which will start when it starts and when it stops. And so we build a small library which hooks into there. And so if you set this environment variable, you can also activate it manually. Whenever the garbage collector is invoked, it will trigger a range and will show up here. And this was actually the reason I actually built this was because I wanted to see when the garbage collector was being invoked in MPI processes. And so it's very nice for this. So you can see here we have all these things, and suddenly everything stops. One process here is stuck in an MPI wait all. That's because it's waiting on communication from this top process, which is doing a GC. So that was what I wanted to be able to find out. And yes, and many thanks to Valentin for pointing out that hook. That was very helpful. And as you would expect, it supports CUDA and CUDA.jl. And so if you just, it will show the CUDA kernel launches along top. So you can see now there's an extra CUDA API line here with the CUDA kernel launches. And it traces, what's nice is it traces both the CUDA activity on both the host and the device. So these are the In particular, you'll see this little box here. You have to expand that out because it matches the ranges both on the host, so those range annotations are on the host and the device. And often, you typically want actually what is happening on the device. And to give you an example, is that what's happening on the host can be very deceptive. So in this particular example, if you look at the top one, you would think this blue box is probably the worst one. But when you look on the device, you can see it's actually these red ones. The blue one's almost negligible. It's this tiny gap here, and the red ones are actually what's taking up all my time. So make sure you click that little expand button so you can see what's actually taking time. Minor usage tips. The profiler does have some overhead itself. In particular, this tends to appear as sort of frequent pauses. I think we saw about 1 millisecond every 60 milliseconds or so. And the easy fix here is just to make sure you have an extra CPU core assigned for your profiler. If you're doing this on some sort of cluster, there's typical ways to reserve cores and bind the cores to, so you can, if you bind the cores to each task, that will ensure that everything gets sort of, assigned nicely. The profiles can get very big, so don't try and run it for too long. NVIDIA say they only support up to 10 minutes. It will go longer. You'll just get very large files. And there's a neat feature. You can export the profiles to SQLite, so you can do sort of analysis for that. Related efforts, there's other profiles out there, other parallel profiles as well. ScoreP by Carsten. So ScoreP is a big, ScoreP.jl, which is interfaces with ScoreP, by Carsten, who's is a very similar MPI type profiler. And there's Intel. I'm not sure. So someone pronounced it Itapi yesterday, but the Intel ITT API, which is Intel's sort of instrumentation for Intel's vTune profiler. So Valentina and Tim have done a fair bit of work wrapping that as well. And I mean, so there's also been, there's been a lot of effort recently on instrumenting the Julia runtime. So that's separate than the GC one I mentioned. I would love to be able to hook into that. So currently there's Tracy and Intel ITT support for that. And we've just had some discussions about how we could build a sort of generic interface so we could also profile the rest of the Julia runtime. And then some other things I'd like to tackle. Interactive profiling. You can actually do this through the CUDA package. CUDA at profile will run that. We'll let you do this interactively with the REPL. But I should probably put this actually in the MVTX package as well. We mentioned the common instrumentation API so that other packages can instrument and then use different profilers. And finally, some sort of profile analysis tool for similar benchmark tools and get you the nice histograms.
I'm going to have to call time there.
Thank you.
Thanks. All right, the next speaker is Roger Lowe, who's well known for his work on quantum computing. But today he's talking about metaprogramming. Julia, making physicists do metaprogramming since 2012.
Okay, sure. Should I start? Hello everyone, thanks for attending my talk. Today I'll not talk about any physics. Metaprogramming, we made a collection of tools for metaprogramming. Before I start talking about this package, I'd like to talk about some history back to 2019. So in parallel of working on quantum computing stuff, we worked on something about supporting the features of ML family of languages to Julia. So that mainly includes two things, algebra data type and pattern match. And pattern match seems to be the most popular feature. This package was created by Tanner Zhao, who is a close friend of mine. We have been using MSDL for metaprogramming for quite a long time, mainly used for pattern matching on Julia ASTs or pattern match for custom AST structures that represent some Julia AST, or we also use pattern match to do code generation from a pattern of we matched from Julia AST. So on the right-hand side is an example I copied from ML-style documentation. Here we can see that you can natively use ML-style pattern matchers to match some existing Julia EST like this. This match structure definition, and then you can remove the lines of this expression and check if they're equal. Although ML-style, so in case you don't really, you haven't had this used the pattern match before, to give you a little bit feeling what this is, you can understand this as a reverse operation of constructors. So here's another example of matching Julia expression constructors. So instead of, so on the left-hand side, those are exact the same syntax how you construct a Julia expression using the constructor. But in the match context, we will do the reverse operation instead. So here, instead of construct this expression by inserting the value of A, we will give you the value of A. And underscore means we don't care about that value, which is that's just a wildcard. So although ML-style has been a very powerful tool in metaprogramming, it has been a little bit painful that we keep rewriting a lot of common patterns, and there's still a lot of tools missing we find frequently used. And there used to be macro tools, but we find there's some new things based on ML-style is missing from there. So we start write this package Expronicon as a collection of metaprogramming tools on top of ML-style. So we provide some better AST manipulation APIs based on syntax objects. For example, on the right-hand side, we provide a GL function structure that allows you to construct or directly pattern match a Julia function expression. For example, here I can just match, if this pattern match will just check if the expression is a function expression. If it is a function expression, we'll extract the function hat to you, otherwise return false. And these are combined with ML-style pattern matchers. The other example is you can easily generate nested if-else statements by just using this dictionary interface, while in the normal Julia expression API, you have to do this recursively. We also provide some other tools that we'll talk in the following, that is AST validation, generation, and extraction tools, and also type-stable algebra data type as a very experimental feature. And the other tool I would like to highlight is the testing utilities for metaprogramming. So one thing we found very inconvenient is when you test metaprogram generated expressions, there are a lot of redundant like line numbers that you don't really care. But when you actually use the equality relationship between of the default expression, the return false, which makes sense. They're not exactly equal. What we actually want to test is if they are semantically equivalent. So we provide you a macro that check this by matching a bunch of patterns we think semantically equivalent in Julia, like we will ignore line number nodes. So so you can just use this macro to test if your generated expression is equivalent to what you expect, up to ignoring some line numbers, etc. And the other convenient tool we built for metaprogramming is pre-printing for Julia AST. Although the base printing is nice, but without some basic syntax highlights, it's still hard to read when you generate complicated expressions. So here I would like to show you a live demo. Here I use the live version of Expronicon. I'll explain what that is. So what we're going to do is we're going to macro expand macro from configurations package, and then we print it. So this is the default printing of a Julia expression. And this is our pretty printing. So it used a similar syntax highlight in your terminal as how you use it in your VS Code, and the color is configurable. We print out the components based on their semantics, so it's much easier to read when you're trying to do metaprogram. It also, yes, skip the line number noise. And so the other issue we have is for some applications trying to use Xpronicon, we suffer from latency issues because ML style is a very complicated package. It has a lot of things inside. Before 1.9, this is quite obvious. So we bootstrap Xpronicon by compile out all the pattern match macros, so that Xpronicon, so that we get a package with 0 dependencies. So if you run the using 1.8 and previous version of Julia, you can see Xpronicon Lite is extremely fast to load. This allowed us to use on some latency-sensitive applications like the CLI generators, like configuration parsing. Some get a lot more worse in loading, unfortunately, after 1.9 with the package image. The other reason why we want to use this is, comparing to other tools, is this is actually a very battle-tested package in real-world metaprogramming. So we have been using this extensively across many packages that need complicated metaprogramming, like configurations that we generate the configuration parsing code for you, Command-Con, which is a CL generator in Julia that generates a dependency-free CL parser, and some other quantum computing stuff. Okay. And last experimental feature is type-stable algebra data type. It's like in Nums. It's actually like Rust in Nums. But here, with some trick, we make it type-stable. But this is very experimental because we use some evil stuff like unsafe load. Here I would like to shout out to Mason Poulter. He also worked on a lot of these, and I get a lot of inspiration from his implementation. So some future work. So we now realize ML style still have some limitations in terms of semantic design and some corner cases of the matchers. So we like to rewrite ML style in case of in consideration of that, and also want to bootstrap ML style so that we can use pattern match to implement pattern match. That will make the code base much easier to use. Any questions?
Yes. So I've been reading Julia's AST as part of working with syntax.io. With this AST things, so you mentioned that if else AST is nested, then it's like irritating to work with maybe. So I've been rethinking a lot of those things and have alternative AST. So would you like that one because that's nested? And if you have other ones that you think are awkward, then I'm rethinking them right now. So I'd love to talk to you about it.
Yeah, nice. I'll command on Julia syntax.
Yeah, see juliasyntax.jl. Yeah. And we've got to keep moving. So thank you, Roger. Yes, and believe it or not, Lilith is back. It's not a misprint. We got a teaser earlier about the Scratch quicksort algorithm, and now we're going to get to find out what it is. So, cool.
Lovely. Okay, so Scratch quicksort. It's like a variation on quicksort. It's often, even usually, faster than Quicksort, and it's stable, and it's comparison-based, so it just like works for everything. It's not like a special case thing. And it requires scratch space. So yeah, that's a drawback. But I think it's worth it. So Quicksort is a pretty cool algorithm, pretty quick. It sorts things. So if this is your input, it's a divide and conquer. So it like partitions the input into the things below. It picks a pivot, say 4, just like picks a random element, or I don't know how it picks it. I do know. But let's say it picks 4. Then it partitions all the things below 4 to the left and above 4 to the right. And the way Quicksort does this is by looking at the first first switching the pivot to the beginning to get it out of the way. And then looking at the first element and seeing if it's below the pivot. It is. And the last element, 9 is above the pivot. And 2 is below the pivot. So they should be swapped. 2 should go at the beginning, 9 should go at the end. So we swap those. I grade them out because we're not going to touch them again. And then it'll again look at 7. Okay, that should go above the pivot. 5 should also go above the pivot. It's currently at the high end, and so we're going to leave it there and move on to look at 6, still above the pivot, 8 above the pivot, 1 below the pivot. Now swap these. And then when you're done, you swap the pivot back to the middle. And that's Quicksort. Been around forever. Scratch Quicksort is very similar. We still pick a pivot. However, this next pass, I think, is conceptually simpler. And I think that compilers and hardware think it's simpler too, because it's faster. So you look at 8, and you say 8 is above the pivot. And then you look at 9, and you say 9 is above the pivot. 7 is above the pivot. 3 is below. 1 is below. 6 is above. 5 is above. 2 is below. It's like you look at each one, and if it's above the pivot, you put it at the top. And if it's below the pivot, you put it at the bottom. Very straightforward. The pivot ends up in the middle. So yeah, let's talk about stability. Stability in sorting means that two things that are compare equivalently aren't reordered. Quicksort is unstable, and it's pretty tricky to make it stable, but Scratch Quicksort does make it stable. So to have a notion of stability, you need things that compare equivalently but are distinguishable. So here we have a bunch of 8s that are distinguishable, but they're all none of them are less than each other. These are definitely all fair use, no copyright images, I think. I actually tried to make sure that was the case. I hope I succeeded. Anyway, so same algorithm as before. Select the pivot, and then place the things that are above the pivot above, and below the pivot below. And, let's take a look at this 4. This 4 is below the pivot, because there's a feedback, whatever. Anyway, because we break ties here based on the index. What we really do is when we're iterating over the first half, we check if the pivot is less than the thing we're comparing. And in this case, it's not less than, so we put the thing we're comparing at the beginning. And then we skip over the pivot, and then for the next one, this next 4, we compare, is the pivot, or is the thing less than the pivot? I don't know, I'm getting these things backwards. The gist of it is that we break ties with the index, but we don't have an extra comparison, because we're breaking ties the same way a bunch of times in a row, so we just have a quick loop, and then a different quick loop for the second half. So let's look at, is this a stable sorting algorithm? Is this a stable partition? If we look over on this side, yes, it is stable over here, because how we got those 3 things is we scanned over the input and looked for the first things, looked at all the things that are less than 4 in order and just plopped them in. So that's stable. Nothing got swapped. Now if we look at this side, no, very much not stable. Everything got swapped. Everything? Yes, everything. We started at the beginning, and the first thing went to the end. The second thing went to second to the end. Third thing went from the third to the end. So they all swapped. Fortunately, we didn't lose any information. When everything swaps, you still preserve all the information of what the input order was. And so we can just use we can do this recursively and just keep track, are the things in the correct order or are they in the wrong order? And we never get into they're all mixed up state. And for that reason, we can do a very efficient post-processing that just like flips half the stuff at the end. And the runtime of making it stable at the end is very little. So that's how it becomes stable. Performance, here's some little benchmarks that I ran. These are, caveat, very small domain. There's a lot of different benchmarks you can run for sorting. I'm just pointing at a couple. This is not a representative sample. But the gist of it is Scratch Quicksort is much faster than Quicksort in this case. I'd note here, 4 minutes, lovely. This is kind of a silly benchmark though, because if you just sort using radix sort, which is the default in this input, it's so much faster. So let's look at a different use case. Now I'm sorting with the by keyword set. So we're sorting these by their absolute value, which means we can't use radix sort because we haven't made radix sort work for that and probably never will. Anyway, another silly thing is that I'm showing these results in a REPL instead of a table. So this is better. Looking at, also merge sort is also relevant. If you want a stable sort, quicksort isn't going to work. So maybe we should be comparing this to merge sort instead of quicksort because they're both stable. Anyway, if you compare to quicksort, it's great. If you compare to merge sort, it's even greater. There are some cases where it's slower than quicksort. There are some cases where it's like a tiny bit slower than merge sort, but those are hard to come by. Allocating unnecessarily, huge red flag. Don't do it. Bad performance. Allocating necessarily can actually be fine performance, I think. Although there's some domains that really don't want allocation. And yeah, sorry to those domains. Tricky, I guess. Limitations, it allocates not always faster. I'd like to thank Peter Michael Sarah, Nicole Eichenmeyer for funding, and lots of folks helped review this. So yeah, thank you. Questions?
All right, we have time for a question or two.
Yes.
Oh, I have a dumb question. I just asked my question.
Yes.
What do you think was the like prediction, the memory sum system or whatever, like knowing that scanning very nicely costs us like branch prediction, or which like kind of thing is this?
Yeah, the question is, where do you think the performance comes from?
Yeah, so in theory you could use fancy instrumentation to find out. I can guess that in this normal quicksort, the comparison order, first we're comparing this 9 with the 4, and then we're comparing the 2 with the 4, and then we swap them, and then we compare the 7 with the 4, and then we compare the 5 with the 4, and then what's the next comparison here? It's the 6, and then the next comparison is an 8. Like, the order of what we're comparing depends on the previous comparisons. That feels like it's bad for prefetching. Yeah, whereas with Scratch Quicksort, we're first going to compare the 8 with the 4, then the 9 with the 4, then the 7 with the 4, and like vroom, and it's, so the, maybe it's that? I don't know is the answer.
All right, thanks.
Thank you.
All right, the next speaker is Sebastian Fitzner from Julia Hub, who's going to talk about something that really needs no introduction. Most of us probably use it every day, if not every minute of every day. Update on the Julia VS Code extension.
All right. Yeah. All right.
Yeah, hey everyone. I'm talking about the Julia extension for VS Code today, and specifically about what's new, what has happened over the last year, since last JuliaCon, when we also gave that talk. Turns out, not much has changed. Neither David Antoff nor myself had too much time to spend on increasing the feature set of the extension, although it has been kept, maintained, and as such still works, even with recent Julia versions like 1.9. However, there's one notable exception to this. Some development has been put into test item runner.jl and the test integration of the extension. So if you're among the folks who write tests for the packages, then that's good news, because with this integration, you don't have to run all of your tests at the same time and can instead, pick out certain test items, features you want to test, and fix your tests for. That is a sidebar item in VS Code. I can show that to you later. All right, so yeah, I'll just pivot this talk a little bit, and we'll talk about the VS Code extension, its internals, the good, the bad, the ugly, for some definition of good, bad, and ugly. The good is pretty good, the bad and ugly are not all that bad or ugly, but there are certainly some problems. All right, some good stuff. Code execution, plotting, all of that works, and it works pretty well if you want to use it at least. We have inline evaluation. You can plot your results. All of this is fully dynamic if you're using the right backend for plots or if you're using WebGL Maki. You can run the profiler. You've heard to talk about profilers. This is just Julia's stock standard sampling profiler. But at least you get a nice GUI for it and some integration into the editor, so you can click back and forth and see the relative impact of certain lines of code. We also support the location profiler, which is a fairly new thing, right? It got introduced in Julia 1.9 and works very similarly, at least in regards to the integration in the extension. The test framework I already briefly talked about. Obviously, it's not a well-advertised feature, judging by Stefan's reaction to it. So we'll have to do something about it, but please feel free to use it. Ask questions on the usual channels, if you have any. IntelliSense, which means code completions, documentation for functions or methods or objects in the editor. All of that works fairly well in most cases. Some caveats are around as well, which I'll talk about in a minute. And generally, this goes into the implementation a bit. All of these static features are powered by languageserver.jl, which is a Julia package we wrote. And well, that's sort of the backend that powers all of the static analysis, IntelliSense, all of that good stuff. It's a pretty good package. It conforms to the spec, which is good. And yeah, it serves its purpose. Some of its dependencies, however, will show up later in this talk, which I guess you know in which category that will be. Yeah, another thing I'd kind of like to talk about is the debugger. I've tentatively put it into the good category, even though at the survey talk this morning, people talked about the debugger being too slow and so on and so forth. I mean, true, but also, what can you do, right? It kind of works. All right, let's also talk about a few bad things. It's not entirely clear what the distinction between bad and ugly is, but the title was catchy, so. Okay, false positives, correctness. This has bitten a few people. We have some issues with correctness of static analysis. Some of that is due to bugs in our code base. Some of it is due to the fact that Julia code is fairly hard to statically analyze. But yeah. What's that? So yeah, you frequently end up with these like 12K plus problem badges in VS Code, which makes the feature basically completely unusable for large code bases because, I mean, who has time to look through 12K issues? Macro handling. Macro handling is tricky. I don't think we can do it correctly in the general case. But if you have like this add parameters macro from modeling toolkit, then that introduces bindings, which we should in theory be able to propagate through the rest of your code. In practice, we can't. We just give up, except for like 3 special case macros. What else? Environment handling. This is also a bit of a pain point. In particular, we are not handling stacked environments correctly. Some people have expressed interest in us handling load path, which allows you to sort of side load packages outside of your environment. And something for the testing enthusiast among us, the test directory currently doesn't get any IntelliSense. We've disabled it because it, for the most part, doesn't work in the current implementation. But that's actually really annoying. Performance is sort of adequate if you have small code bases for some definition of small. For large code bases, it gets pretty bad. There are even some pathological cases like generated Julia files where the language server basically shuts down completely and you don't get any updates, or you get updates on the order of like 20 seconds or whatever, which is pretty bad if you want to run that update loop for every keystroke. Most of us probably type a bit faster than that. All right, a few ugly points. And when we think about ugly, then we usually think about code, right? So there's some ugly code in our REPL handling. Basically, we have some issues with integrating interrupts into the extension, basically. That's not just due to Windows not having any signal handling. It's also due to the fact that, yeah, it's a bit unclear how to interrupt Julia code properly from another process without killing our own functionality in the process. Extending REPL functionality is a bit hacky, right? There are some hooks you can use to extend REPL functionality, but in general, it doesn't feel great, and the REPL API, I mean, there's no API for the REPL, right? We are mucking around in Julia internals here. Then there's also the issue around dependency injection. So we have to run some code in the Julia process that the user starts their REPL, and we need to take a lot of care not to prevent them from loading another version of a package we're depending on. All of that also feels a bit iffy because it sort of sidesteps Julia's package loading. All right, now dependencies of language-server.jl. We have cstparser.jl, which parses all of your code into a concrete syntax tree, and then that allows us to run our analysis logic on top of that. That package is fairly hard to maintain, and crucially, it's not the reference parser. Or, well, one of the two, right? We have Julia syntax nowadays, which I very much hope to use in the future. Staticlint.jl is a package built on top of cstparser.jl, and that's what handles a bunch of logic around resolving scopes, bindings, providing completions, providing, well, linting, it's in the name. That package is even harder to maintain than cstparser because it's less straightforward. And there are a bunch of correctness issues in our scope and binding handling logic. And it also kind of has the same issue as cstparser in that it's not the reference implementation, right? The Julia compiler, or steps before the compiler, all handle this correctly, but we don't really have a way to hook into it currently. All right, just briefly, what's in the future? Some high priority improvements I'd like to spend some more time on is, well, as said before, replacing cstparser with Julia syntax. And then rewriting parts of staticlint on top of that, just for correctness sake. Speculative improvements around features. There's been some asks around plots, making them better, and the debugger, of course. All right, if you want to help out or complain, feel free to find me or reach out to us on Slack, GitHub, or Discourse.
All right, just on time. Thank you. Okay, and the final speaker of the session is Stefan Sam. Are you here? Oh, great. Okay. Yeah, we're just gonna move right on. So Stefan has his own Julia consultancy, and we're going to get to peek into his personal toolkit and look at some of the utilities that he finds convenient.
Thank you very much for the introduction. So, there we go. I want to show you 3 little tools of mine. They're really tiny, and 2 of them are pretty old by now already, but it seems like I'm almost the only one using it, and I want to change that. So yeah, let's see. Maybe the one or the other fits also into your toolbox. So I'm Stefan. We have full screen. Yeah, looks good. Stefan Sam, Jolin.io. You can check it out. There's also a recent product launch at cloud.jolin.io. Yeah. I'm welcoming any testers. Let's start right away. So we have 3 packages: simple match, not macro, and proxy interfaces. So first one is simple match. That looks a bit tiny. That's okay. Yeah, I won't do this the whole time, but at least kind of for the beginning. I have some Zoom specialty. This one was kind of started to get something like match, and we've seen it just a couple of presentations ago. There is ML style, and there are other packages which give you a match function where you can kind of somehow deconstruct things, and they have been just too complicated for me in the beginning. I wanted to have something very, very simple. Yeah, so they are all fancy and great, but it just looked too much for my mental life, and I wanted to have something simple. And the simple thing which is there in Julia, which you know by heart, are these functions. They do already kind of some kind of matching, yeah, this dispatch. And yeah, I like them, I use them a lot, and this would be kind of one style how you can use this for matching, yeah. For like you just define your inner function, and yeah, it's kind of okay, but you have kind of this reversed order, first defining the function and then calling it to dispatch on it, and you also need to come up with a nice name. So yeah, these are kind of the 2 things which simple match is going to solve for you, and this is it. Here it comes. So if you make using simple match, you get access to this little match macro, which is really just rewriting this code to get you yeah, inner function with an anonymous name. And yeah, and the syntax I've used here is this do syntax. This allows like for normal function call. Yeah, in this match parentheses, you really put whatever arguments you want. You can have splashes, you can keyword arguments and all the like, and it's really just forwarded to this inner function. And using this do style, it's super intuitive that this is now really an anonymous inner function. So this is why I really like this style a lot. But I want to have kind of care about the function names, and you also have this order, like typical for a matching style. You first define what you want to match, and then you define the cases. And yeah, so I hope you passed this example here. So we are inputting a value type, yeah. So a value. So and we can kind of dispatch on it, and this is kind of an expression example. So we get the head and use Julia's dispatch to get all these cases. But you can use it for arbitrary objects. This is really just function syntax. Okay, so super tiny package. Maybe it's also something for you. Check it out. This is simple match. Okay, going to my next little one is not macro. I have to admit I'm not using this a lot, but still for me it felt like, I want to have this. So, little disclaimer, of course, I know. Julia is not Python, and that's good so. And I myself came from the Python world, and I love Julia. For a little extra note, there's a really long discussion on adding and, or, and also not, yeah. And this is clearly answered with a no, yeah. So there won't be these things as Julia syntax. So you stick to these little and or yeah, how to spell them. This is fixed, but not you can get, and this is because not is just kind of at the very base. It's lowest binding, so we can write a macro which does this, and this is it. So here's not macro, and yeah, you just use it like not, but put an at in front. And this works because we can restructure the code so that it actually follows the strict binding. So usually every macro gets all the stuff in it which follows after it. This is of course not the semantics here, but the implementation of the not macro now follows the standard semantics. I hope you get what I mean. So if we macro expand it, you really see that we just have our normal negation in front of everything. But the semantics of the macro, of course, they work differently. You get the entire thing as the first part, and now we need to restructure this. And this is why there's a package for it, So it's not super straightforward to write it on your own. So you need to do some checks that this is really kind of well done, and hence there's this little package. Okay, so if you like to have not instead of exclamation mark, that's for you. Thank you. Last one, proxy interfaces. And this, I hope, is really going to be used much more, or something similar around this. So the thing is that we have all these nice, we have the separation between types and functions in Julia. And this is really awesome, so we can kind of build whatever we want. And one thing is like a proxy. So this is a little example. Now this is a type which adds something on top on the normal dictionary. But I actually don't want to re-implement the normal dictionary, so I proxy just everything else to this dictionary, which I store inside my proxy type. So I have my dict over here. And and now I need to re-implement every single dict function. So that gets tedious, and this is a lot of work. It actually may be that as of now there are also some other packages out there, but I haven't found them easily. So this is mine, already a bit older, to just have a nice general layer which simplifies this for you, where we can kind of keep a couple of these standard interfaces. So how does it work? You use proxy interfaces and you specify a mapping for the type and you specify a mapping for the value. So these two mappings are needed then, and then everything can be kind of automatically constructed for you with the respective macro then. So this would be the way for our little example. And that works. So we get then access to indexing and other dictionary stuff. So it's really 3 lines usually. And so one example. That's a default dict, just overwriting the get index to have a default value, and getting all the rest kind of from the struct now dict mutable to get also the mutable stuff. I intentionally made them distinctive, so the normal one is not without the mutable stuff. And now, you get this, and it works, and of course your extra definition is taken up because it's defined afterwards. Okay, so this is the overview of stuff which is implemented. Not too much, but still very useful for me, and hopefully for you too. So we have the dict, the array, indexing still separate, and iterator. These are kind of the standard interfaces you also find in the Julia documentation. And I'm very happy to add others. Pull requests welcome. Also, if you have it's kind of common to miss up some function because they are spread all over. So if some dict or array function is missing, it's super easy to add them up, even within minor version changes. Okay, last one. There's also another famous macro which I put into this package as well. There's this forward macro. It was here and there recursing, and this is now also one place where it lives. So it's just a flexible forwarding a specific function to a subfield. But this is then by the generic dict or array macro. There's no longer needed. Okay, so this was proxy interfaces. And so simple match, not macro, proxy interfaces. I hope some of this also fits into your toolbox. I would welcome some stars. I would welcome some code commits, anything. And last note, check out cloudjolin.io. That's kind of my work for this year. Yeah, this is really awesome Pluto deployment, maybe also for you. Thank you very much.
All right, thank you, Stefan. Yeah, that's pretty cool. But if you know how macro parsing works, then not macro is mildly cursed. I just have to say, if you.
Do we have time?
I guess so. I guess it works. Any questions?
So if I say A ampersand at not B or pipe C, doesn't the not eat up everything after the ampersand? And so it seems like it would be impossible to properly parse that.
Yeah, the question is, does the not macro eat up everything after it? And yes, it does, and that's what makes it tricky.
Yes. Yeah. Thank you. Yeah, and this is why there's this page. So yeah, so you need to restructure everything so that it really is at the first place. Yeah.
All right. Well, thank you, everyone. That is the end of the session. I am only 9 minutes behind schedule, but the committee padded it by 10 minutes, so I'm actually 1 minute ahead of schedule. Woohoo! It is now exactly 5. Remember the poster session on the 4th floor at 6 p.m. with free food. Thanks to all the speakers, and thank you, everyone.